问一下，那个有准备好了吗？好，各位先进大家好啊，我是叶兴公司夏安宙。那今天很荣幸的在周二的下午这下半天的课程啊，来为各位来导读啊。那其实说导读也不是什么特别的导读啦，我想就把几位的讲者稍微介绍一下，然后大致上我会分享一下我在台湾做调查这些20多年的经验，在我的看法是怎么样。那我们的下午总共有四个课程啊，那是由3位美国环保署的专家来，他用录影的方式来帮我们上这个课啊。那前面2堂主要都是一些现场采样土壤跟地下水采样跟分析，还有一些现场筛测的工具啊。它分为土壤跟地下水，这是前面2堂哦。然后第3堂就是说很重要，就是说我们做调查的目的，做这个高解析度的场址调查的目的，就是为了要后面的整治规划所用。所以怎么去运用你调查出来的数据去做后面的整治规划，去把它优化，让你的整治工作能够更有效率，甚至让你的整治经费可以更节省的情况下去做好这个调查的工作啊。那第4个就是他会介绍一下说，这个高解析度场址调查它的优缺点啊，它的优缺点，还有它的资料的判断，我觉得这个很重要啊。那我在这边也分享一下啊，其实高解析度调查，在我认为就是我们当做就是说，在有限的资源下，你怎么取得现场更多的数据？那这些数据是你未来在做整个场址，不管是风险评估或者是整治规划的时候，这些数据你都可以用得上。再来说，这些数据你都是可以信任的。所以我们调查结果尽量减少产生那种没有必要的数据，说那个数据对你来说可能一点意义都没有。你还要就因为没有太多意义的数据，你花了很多的钱。但实际上这个东西并不是你们要的，所以我们在做调查规划的时候就要去思考。我常跟我们年轻的同仁是说，你在做调查规划前，请你先想好说，你未来的调查评估报告里面要出现哪些的表格，哪些统计的数据，你们想好以后去做规划，这样子你未来的报告才不会说做完以后发现这个没有做到，那个没有做到。再来是说，是不是第一阶段就要全部把调查做完？还是说可以留一点点扣打，我们再做第2阶段的补充调查。因为往往我们调查目的是什么？第一个，它的污染的浓度的高低嘛，第2个，它的范围，它的水平的范围是到哪里，深度是在哪里然后它的量，这个是我们在做高解析度调查，其实最终的目的大概只是你要取得这样的一个参数，最后面的参数，再加上现地的水文、地质的各项参数，所以你要综合起来看这个事情。那今天下午课程他们就会讲的比较比较实际一些了就是说他用的工具，他用了各项现场筛测的工具，怎么样去增加你现场的数据，然后这些数据你要怎么用，怎么去判断它的好坏，它的相关性是什么。OK， 好，那我想。第1堂课是这个Tim Friedrich 那 Tim 我介绍一下，他是在美国环保署的第4分区一个 Super Pond 的部门当做一个主管他也是美国东南部的污染场址专案的管理人员。那他的专长是公共卫生。环境风险评估，然后一些水文地质方 方面的哦。那 Tim 其实他在2005年加入美国环保署以前，他其实在外面的顾问公司工作啊，所以他当过很多厂址的整治的负责人，所以他也很了解这个调查跟后面整治的一个相关性哦。那我们是不是现在就来放我们第一堂课的影片 ？OK， 大家来观赏。
Hello, my name is Tim Frederick, and I'm with EPA's Region 4 office that's located in Atlanta, Georgia, in the southeastern United States. There I work in our Superfund program, which is our program for dealing with hazardous waste sites. I'm very excited to have this opportunity to talk with you, and I look forward to sharing our experiences with you. Today I'm going to be talking about an overview of high-resolution site characterization, on-site soil sampling, and analysis methods. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. So let's begin by talking about how we collect soil samples. This table presents an overview of traditional sampling methods, discrete or grab sampling, composite samples, and incremental samples. I'll go more into each of these types of samples and which ones may or may not be suitable for high-resolution site characterization. When we're talking about what type of sampling that we should do at a site to best characterize a site, our data quality objectives are key. We need to understand upfront what the purpose of the sampling effort is. We should carefully consider how the data will be used to inform decisions. Are we just wanting to know if contamination is present or not? Do we want to fully delineate the nature and extent of the contaminants in the soil? Are we collecting data to inform risk assessments? Are we collecting the data to confirm that our removal has been fully completed and meets our cleanup objectives? We might want to do different things for each phase or each type of sampling. HRC sampling seeks to address the scale of the sampling. What's the size of the area that we need to sample or reach some sort of decision about? We need to think about sample spacing and density. For high-resolution sampling efforts, we generally want to have our sample spacing reduced and have high-density sampling. And those two things can help to inform where those samples should be collected. It helps to take a moment and think about our goal of soil sampling. The goal of most soil sampling efforts is to collect a sample or samples that are representative of the area that we want the data to inform. If the data are not representative, it can lead to bad decisions. We want to make sure that the soil that goes to the lab adequately represents the area that we're sampling. Soil is a problematic medium because of its inherent heterogeneity. In soil, heterogeneity is the rule. The picture on the far left shows the number of possible samples that could be collected within a single square foot area if we're using a 2-inch sampling tool. It's about 36. The next figure to the right shows the variability of samples that were collected for uranium within a single square foot sample area. The data vary widely, and as a result, they could lead to differences in decisions based solely on chance related to the sample location. Similarly, the figure on the right shows data collected on a 1-foot interval on a transect for arsenic. Again, these data vary widely and could also lead to differences in decision making depending on the sample location selected, if we were only selecting one of these sample locations. Overcoming this heterogeneity can be a challenge and is the goal of HRSC soil sampling efforts. One of the reasons for soil heterogeneity is the variability of soil particle size within any given sample and which fractions are selected, intentionally or not, for analysis. In the photo above, an unprocessed soil sample was passed through a variety of sieves in the field. The resulting size distributions can be seen in the picture. We can see that we have very coarse soil particles ranging all the way on the right, all the way down to very fine soil particles on the left. Taken together, these samples would create a sample that have a great deal of heterogeneity just in composition. Discrete samples can be collected from biased or from random sample locations. A discrete sample is collected from a single location. The sample volume and additional sampling processing can vary accordingly. Discrete samples are easy to collect and may be useful for collecting information about a specific area of interest, such as a visible release. Discrete sampling methods do not typically address the potential heterogeneity of the soil. High density of discrete samples could be collected for HRC applications to determine the potential distribution of contaminants across an area of interest. However, we would still expect the between sample concentrations to be highly variable. A typical composite sample is assembled from a small number, like 5, discrete samples that are combined in the field. The component discrete samples are typically collected in a quincunx pattern or a die pattern, as is shown here, that may or may not be of equivalent size or mass. The samples are typically mixed in the field and placed in the sample containers specified by the analytical method. The sample volume and additional sampling processing can vary. This method is not very rigorous typically and is not usually used in HRSC soil sampling applications. Incremental samples, also called incremental composite or multi-increment, are structured samples that provide an unbiased, reproducible estimate of the mean of a given volume of soil, what we typically call a decision unit. An incremental sample is assembled from a large number of small samples, 30 to 100, of equivalent size or mass that we call increments. They're collected from random or systematic random locations across the decision unit. The process typically yields a large sample mass, greater than a kilogram in most cases. Additional sampling processing in the field or laboratory and subsampling is usually required. Incremental samples are collected with specialized sampling and subsampling tools that are needed to properly sample and subsample the soils. I like to spend some time talking about the ISM method because it's designed to address the inherent variability in soil data and is often used in HRSC sampling applications. This figure provides some additional detail on how incremental samples are constructed from multiple increments. We can see that there are circles, X's, and triangles across here that are representing individual increment locations. So if we begin with the circles here and collect an increment here, each place that we see a circle, and move through the sampling area, systematically collecting each of those, an increment at each of these O locations, we see that they come over here and are used to construct a sample. Similarly, all of the X's moving through space are collecting increments moving systematically through the sampling area, and likewise the triangles, we can move through each of the triangle locations and construct a third sample. So although there are many increments that are collected to construct these samples, we end up with 3 samples that are analyzed. These are called replicate samples because we're replicating the process of sampling systematically and rigorously the area that we're sampling, called the decision unit. The systematic, rigorous process is designed to minimize sampling and analytical error. So we're going to get data that are reproducible, and we can evaluate these replicate samples to see how reproducible are. We can quantify the variability between these samples to let us know how much heterogeneity is in the soils that we're sampling from. This is a figure from a paper that I wrote with some others about incremental sampling, where we were for a research project, and it demonstrates how the incremental sample can be constructed. So here we have a quarter-acre decision unit. A decision unit is the area that we want to make some decision on. Each of these grids is sampled. You can see that here I used a circle, a triangle, and a square that represent the 3 increment locations. These locations within each grid were selected randomly. We used a random number generator to come up with these coordinates, which we're able to measure to make sure that we're being systematic as we moved from each grid. So in each grid, a increment would be collected, a same-sized increment would be collected from each of the locations where the circle is all the way through to carefully construct our 30 increment sample, similarly with the triangle and again with the square. So we would have 3 samples at the end. Incremental samples are typically collected with 30 to 100 same-sized increments collected to build one incremental sample within a decision unit. The number of increments is typically based on the expected variability, not the decision unit size. So if we went from this quarter acre to a full acre, we could use the same number of increments if we suspected that the variability would be similar in the larger DU. Sampling design should be site-specific and based on data quality objectives and systematic planning, like any other sampling process. Let's talk briefly about some of the differences between discrete and incremental sampling designs. The figure on the left represents a quarter acre to be sampled that has been gridded, and 3 randomly selected samples, shown here as red triangles, have been collected to represent the sampled area. This could be a typical non-HRSC sampling approach. The results are likely to be highly variable. The figure on the right shows how 2 incremental replicates are being constructed across the same sample area. This high density of the increments, in this case 100 increments, demonstrates how the ISM samples, which involve same-size increments, are able to better represent the unbiased mean concentration across the sample area than the limited number of discrete samples shown on the left. If a more detailed understanding of the distribution of the contaminants, the nature and extent of the contaminants across the space is needed, an alternative to ISM might be to collect high-density discrete samples, for example, collecting all of the triangles in the figure on the left and analyzing those samples using an HRSC analytical method such as XRF. The variability of the high-density discrete samples is still likely to be higher than the variability between the replicate ISM samples, but they provide that additional information about distribution. A key component of incremental sampling is collecting same-sized increments throughout the decision unit. This is done so that each increment represents proportionally the overall concentration of the incremental sample being collected. Using a specifically designed sample tool facilitates the collection of same-size increments. It helps to make sure that as you move from increment sampling location to location, that a same-sized increment is collected in each location. The increment mass or volume that is collected is a function of the sampling depth in the sampling tool diameter. It's important to always pilot a variety of sampling tools at your site prior to mobilization to make sure that the tool that you've selected to collect your increments is best suited to the site conditions at your location. These photographs show a variety of sampling tools that can be used to collect same-size increments for surface soil sampling applications. The tools can vary by width, depth, and release of the soil contained within the sampler. The third picture from the left shows a simple hand trowel and stainless steel scoop. This was used at a site after it was found that the soil was too sandy to stay inside of the original sampling tools that were selected for the project. The sample simply was released from the tool as soon as it was pulled from the soil, and we were unable to collect any sample increments. By using the hand trowel and the scoop, we were able to make sure that we had same size increments throughout the sampling area. Clay soils and damp soils can also present challenges depending on the type of sample device that's also used. For this reason, again, it's recommended that a pilot test should be conducted ahead of full-scale sampling at a site, if possible, to ensure that the sample tool is appropriate for site conditions. An important part of developing an incremental sampling strategy is determining the proper number of increments to collect. This decision, as I mentioned earlier, should be based on potential heterogeneity, not decision unit size. As the expected variability increases, the number of increments should also increase. Now, in order to have an understanding of the variability, you may need to collect some screening level data at a site to see what the variability between samples looks like. You may have some other existing data, but you should have some idea of how heterogeneous you expect the soil to be in a given sample area. Typically, 30 increments is a minimum recommendation. 30 to 100 increments, depending on variability, can be collected. The state of Hawaii recommends a minimum of 200 increments when sampling for PCBs, because for a number of reasons, PCB contamination in soil can be highly variable from location to location. And to overcome this heterogeneity, we can increase the number of increments even more, up to 200. So EPA method 8330B says that the error associated with distributional heterogeneity, the way that the contaminant is distributed throughout your sampling area, is inversely related to the number of individual increments used to build the sample. So again, as your number of increments goes up, the sample error that's associated with your distributional heterogeneity is going to go down. So when in doubt, a simple rule of thumb is to collect more increments. Another key component of incremental sampling is collecting replicate samples. Replicate samples, as the name suggests, replicate the number of increments. These use the same sampling tools. They're collected in the same manner, as many replicates as are collected in a decision unit, in order to evaluate the sample variability. We can use this quantified measure of variability to evaluate the precision of these samples, and we can use that information to determine whether our sampling strategy adequately addresses sampling error and heterogeneity that are always going to be integral to sampling in soil. So how many replicates do we collect? Generally, a minimum of 3 replicates are recommended. This photograph shows a sample project where we collected 5 100 increment surface soil samples. We collected 5 because we were collecting some highly variable soil. We were looking for asbestos in soil, which can have a high degree of variability. And so we wanted to increase our replicates to have a better measure of the variability, to see how we were doing, to see if 100 increments was truly enough to overcome that inherent heterogeneity. Again, more or fewer can be collected depending on your site-specific data quality objectives. So let's take a moment to talk about some definitions. Incremental samples are collected within decision units. I've used this term in a few slides without defining it, so let's do it now. A decision unit is the smallest volume of soil for which a decision is going to be made based on ISM sampling. A decision unit could be as small as a residential yard, or it could be many acres. A related concept is a sampling unit, which is a volume of soil from which increments are collected to determine an estimate of the mean concentration for that volume. A decision unit and a sampling unit are often the same, but they can be different, and I'll show you an example in a moment. The selection of a decision unit should be carefully considered. It should be based on what we know about site operations. It should be based on what we know about potential data concentrations from either screening efforts or from existing data. But they should be carefully considered to make sure that we're sampling in a way that minimizes heterogeneity that might be unrelated to the contaminant concentrations that are present. Decision units can be the same or different from an exposure unit. An exposure unit is a term that we use in risk assessment that defines where exposure might take place. So an example that I gave earlier of a residential yard, that might be the decision unit of interest, but it's also where exposure for a child may take place within his yard. So that could be an example of where our decision unit and our exposure unit are the same. Sometimes a distinction is made between a decision unit and a sample unit. Usually, these are the same as indicated in the top figure. The decision unit, the area for which a decision is being made, is the same area that is being sampled. In the bottom figure, a decision is being made in the same area, but smaller areas, sampling units, are being sampled to provide additional information. This is distinct from an area with multiple decision units, which are being sampled separately and for which decisions will be made separately. Decision units can extend vertically depending on our conceptual site model of where we expect contamination to be present. This figure is simplified for readability, but the main idea is that a sample core can be collected and used to understand the average concentrations in different depth intervals that can be designated as separate decision units. A minimum of 30 increments is still recommended. So if we look at one of these cores, this one that is circled in yellow, we see that there have been 30 such borings installed throughout our decision units. The sample interval from this one core, we can collect an increment from the 0.5 to 1.5 sample interval and have that contribute to a sample that will represent decision unit 1. We can then go from the 1.5 to 3 foot interval and collect a separate increment from the same core that can contribute up to, as one of 30 other increments that will be used to represent decision unit 2. We can go back to the same core from the 3 to 5 foot range, collect another increment that will be one of 30 such increments that are used to understand the average concentration throughout DU3, and then we can extend from the 5 to 10 foot increment, interval, to collect another single increment that will be one of 30 such increments that are combined to construct a sample to represent DU4. Again, decision units are that smallest area that we need to make a decision on, and we can construct them in a variety of ways. The picture shows a release area that we may need to make a decision on. Does the concentration within the spill area exceed some regulatory criteria that would necessitate taking an action on the part of our agency? So we can draw our decision unit to represent that area that we can see has been visibly impacted by our spill area to help us make that decision. Decision units can be equivalent to exposure areas. For example, this is a residential yard. We know that children play in this yard. That's where they may be exposed to contaminated soil. So we may want to sample that as a decision unit on which we need to make some decision. Do we need to take action here, or not. Decision units can also be constructed or established based on existing data. In this case, we knew that a soil pile, shown as the box with an X here, contained high concentrations of lead that was from reclaimed waste from shooting ranges. The topography sloped in the direction of the arrow and corresponded to areas of higher lead concentrations from existing samples. The darker circles here are representing higher concentrations of lead in the soil. DU1 was created to establish a decision unit that captured the main area of potential contamination based on topography and our existing data. DU2 and DU3 and DU4 were created based on topography principally. Later, we added DU1A to see if heterogeneity in the field samples in DU1 replicates were the result of potentially lower concentrations in that area. So that was a decision unit that was subdivided for the larger decision unit 1 later, after we had some additional data in hand. When little is known about the potential concentrations or former operations at a site, field screening tools may be useful in determining appropriate decision units. In this example, an XRF is being used to collect in situ readings for arsenic to see if areas of higher or lower concentrations could be quickly identified, and decision units could be developed accordingly and could be sampled by more rigorous sampling procedures. We typically don't recommend using in situ XRF measurements for decision making, but they can help us figure out how we may want to sample a given area and divide it into decision units. Let's look at a few examples of incremental sampling in the field. When collecting incremental samples in the field, it helps to have a clear idea of where the decision unit is, what its boundaries are, how it will be divided to collect increments, where the increments are going to be collected from, etc. In this picture, which was part of a research sampling effort in Washington State, the team wanted to be very clear for documentation purposes. A physical sample grid was laid on the ground using rope. You can see the grid laid out here. Each increment location, which was again selected by using a random number generator that I showed you earlier, to pick coordinates that were applied to each grid square to construct the sample. Each of those increments was identified by a survey marker flag. You can see one here. This level of advanced preparation is not always necessary or possible, but it can help to make things very clear about how the samples are going to be collected. This picture shows a second DU at the same site as the previous slide. You can see that the sample grid is laid out with ropes in the foreground. Higher grass in this area made it much harder to lay out that grid and to place the survey markers for each increment location. However, it was helpful in this case to have everything laid out clearly before sampling, because the sampling team were in PPE, which limited the team's vision and movement. The team is sampling soil contaminated with asbestos that required the use of respirators and other protective equipment. So having the grid laid out in the sample locations really helped the team to know where they needed to go next to collect each of the increments to build the samples. But laying out a sample grid physically in space is a luxury that cannot be afforded at some locations. At some sites, it is just not going to be possible or practical to lay out a sample grid or place the markers for increment locations. In these cases, alternative methods will be needed to keep track of the team's location within the DU and the approximate location of each sample grid and each increment location. In this case, flagged wooden stakes were used to mark the corners of the decision units. The location of the next sample was paced off as the sampler made his way through the brush. GPS was of limited value due to the dense vegetation. Things could be measured off with a tape, etc., but things were difficult. For the location in the previous slide, a laminated sample sheet was used to keep track of the samples collected and ensure that all the increments were collected for each sample. These samples were 100 increment triplicate samples that were collected at the site in this decision unit. Because of the ground clearing required to access each location, this was an effective way for the team to ensure that they didn't lose track of where they were between sample locations. You can see from the dates laid out here that it took quite some time for the team to move through this DU and collect all of the increments needed. So it was critical to have a method of keeping track of where they had been, where they had not been, and which samples needed to be collected. Another advantage of incremental sampling techniques is that the samplers become very familiar with the soil conditions throughout the site. In the photograph above, a coworker and I are collecting 5 100 increment replicate samples within a quarter-acre decision unit in Oregon. At the end of the sampling, we had collected 500 total increments in our decision unit. We quickly learned that although the area seemed to be homogeneous before we started sampling, that it varied in distinct patterns across the site. Some specific areas were sandier than others, some had a more clay-type soil. This type of familiarity with the site could become useful in understanding the fate and transport of contaminants across the area, or could explain unexpected heterogeneity between the samples. But you would otherwise not have this intimate knowledge with the soil in your area if you were not collecting such high density increments throughout the decision unit. Individual increments can be collected with specialized hand tools. In the picture on the left, an incremental sampling tool is equipped with a slide hammer that can be used to help drive the tool to the necessary depth in harder soils. In the picture on the right, a direct push technology or DPT rig is being used to hydraulically drive the sample core to the desired subsurface depth, in this case 12 feet below land surface. The collection of incremental samples can vary considerably in the amount of time collected. On another slide that had dense brush, heavily wooded area, it took a couple of days to collect the increments across that site, across that decision unit. In this yard, a small residential yard, one 30-point composite was collected in about 8 minutes. In the handout version of this presentation, there's a video that I'm not able to show you now and narrate that shows how the sampling team was collecting these samples. But under ideal conditions, a sample team can quickly construct a sample with the desired number of increments. In this case, 2 people are using incremental sampling tools to methodically collect 30 increments across a residential yard. A third team member is collecting the increments in a foil pan. Note that a grid has not been physically placed on the ground surface. The experienced sample team has sampled many yards, and they are able to approximate evenly spaced increments across the yard. For this project, the team has sampled over 1,000 residential yards and have become very efficient at collecting samples quickly and correctly. However, as noted in those previous samples, adverse site conditions can slow down that effort considerably. Regardless of sampling method, our sampling strategy should be based upon a conceptual site model, an initial conceptual site model that lays out our understanding of release mechanisms, potential fate and transport, potential exposure areas, and confirming our conceptual site model through our sampling strategy. The level of sampling needed to do all of that will depend on our data quality objectives, which can in turn be informed by existing site data I'd like to take a moment to introduce you to a website that might be useful to you to help design sampling and analysis strategies for your sites. The U.S. Federal Remediation Technologies Roundtable website, and I have a link at the bottom of the slide, is a good reference that provides very detailed information on methods that are available to access sample locations and available HRSC analytical methods by sampling media and by contaminant classes of interest. I'll discuss some of these sample access and collection methods for soil in the next few slides. So one way to access sample location areas is by drilling. And access here is used to describe the method to get to the soil interval of interest for direct in situ measurements or to obtain a sample for ex situ measurement using HRSC methodologies or to be sent off to a lab. Drilling methods can vary depending on whether the subsurface conditions are consolidated or unconsolidated. They can vary by impact on the substrate that's being drilled through. These methods will be discussed in more detail in the groundwater tools section. Another method for accessing soils for analysis is using drive methods such as cone penetrometers or direct push samplers. Pictured here is a direct push technology rig that is used to collect soil at depth. Typically for ex situ analysis, it'll withdraw a core of soil that can be analyzed in the field or collect a sample that can be sent off to a fixed laboratory. And we've also talked about access tools that are handheld, things like scoops, spoons, shovels, hand augers, tubes that can be driven or pushed into the soil using hand pressure. These are usually used for collecting surface soil samples, and we've shown some of these in our discussion of incremental sampling tools. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. Now let's talk about analysis of samples in the field and field processing that may be necessary to improve on our analytical results of those samples. Selecting tools for analysis can be dependent on a number of factors. It depends on the contaminants. We may need to do different things for volatile organic contaminants than we would do for metals, for example. It depends on the sample access methods, how we get to the sample interval of soil of interest. It can depend on whether in situ or ex situ analysis is preferred and whether the ex situ analysis is in the field or in a fixed laboratory offsite. And critically, it can depend on the data quality objectives, the accuracy and precision that are needed for our decision making or our other sample collection purposes in the field. Some sample analysis tools for VOCs, SVOCs, and pesticides can be broken up into in situ or ex situ sample tools. In situ is typically limited for soil for laser-induced fluorescence techniques. Ex situ, however, we can use PIDs, FIDs, gas chromatography, detector tubes. Again, this can be dependent on our data quality objectives and the decisions that need to be made at the site. Sample analysis tools for metals. We have the very common X-ray fluorescence or XRF tool that can be used to collect real-time measurements ex situ in the field, or in situ if we just want to collect measurements of the surface in place. Increasing in complexity, atomic absorption spectrometry or inductively coupled plasma atomic emission spectroscopy tools can be used in a field lab setup where we can collect these measurements directly in the field without sending to an off-site fixed lab, but we'll need to do some extraction of the soil for analysis. We can use less sophisticated colorimetric kits, and there are some others. Sample analysis tools for radionuclides can vary depending on the type of radiation, whether it's alpha, beta, or gamma. Gamma can be detected from quite a distance away. Alpha and beta radiation will need to be closer to. But we can use common handheld radiation detectors for screening samples. For alpha and beta, it's not recommended for gamma, which has more energy, requires more personal protection. We can use a gamma ray spectrometry. We can use nuclear magnetic resonance, and there are others that can be used in the field as well. And there are some tools that we can set up to analyze in the field for explosives. We can have a field gas chromatography lab set up, a mass spectrometry lab set up in the field. We can do GCMS. We can do ion mobility spectrometry, and some others. Perhaps an underappreciated part of doing field sampling and analysis is the sample processing that can help to improve the reliability of the analysis of that sample. We should always remember that what happens to your sample in the field or in the field lab is as important as what you did in the field to collect it. If you have used very rigorous means to collect a sample, your sample processing should be equally as rigorous. Field laboratory processing and subsampling should also be conducted appropriately to reduce the heterogeneity within the collected samples and to improve the overall data quality. Verification procedures may be required to confirm that the data quality objectives are met. Some form of ex situ sample processing may be required to ensure that high quality reproducible data are obtained from the sample collection effort. Some typical soil processing steps include drying, grinding, sieving, and subsampling. The sample processing steps needed will depend on the contaminant as well as the analytical methods selected and the data quality objectives. Drying samples may be required to ensure that soil moisture is not interfering with the field analytical tools or to facilitate sieving of samples. For example, soil moisture should be less than 20% for XRF analysis. In the picture on the left, electric warming ovens are being used to dry samples at 200 degrees Fahrenheit in a field trailer prior to being analyzed. In the southeastern United States, where I work, temperatures can be very high in certain months of the year. In the picture on the right, collected samples are being air dried in the field on a sunny 94-degree day. Moisture readings can be collected using a moisture probe and recorded to document that the target moisture goal was achieved in the field. Sample grinding may be a sample processing step that can be performed in the field if a goal is to reduce soil particle size heterogeneity. Breaking up soil clumps can also facilitate sieving. In the lab, this is done with tools such as a puck mill. In the field, that type of tool would be impractical due to decontamination concerns. However, soil clumps can be disaggregated by hand pressure using a stainless steel spoon to reduce the size of large soil particles. For some contaminants, such as metals, the fine particles are of interest. Sieving soil samples to separate the fine particle sizes for analysis can be performed in the field. Using stainless steel sieves in the field can be difficult due to the time needed to decontaminate and dry the sieves before reuse. On a recent project where thousands of samples were collected and sieved, the project team solved this problem by using disposable sieve mesh, pictured here. that are placed between easily cleaned reusable sieve collars. This greatly improved the overall efficiency of the sample processing and reduced the sample heterogeneity and resulted in very good correlation between field and lab analysis results. Incremental sampling methods can produce very large samples on the order of 1 to 5 kilograms depending upon the number and size of increments. Accordingly, it's often necessary to reduce the sample volume for analysis by using subsampling techniques. In the photograph on the right, a 2-gram subsample of fine soil particles has been systematically subsampled from the larger 2-kilogram sample on the left that was collected. It's important when subsampling to maintain the representativeness of the sample all the way through to analysis to get the best sample results. To do this, subsampling techniques should be as rigorous as the sampling method itself. EPA has published a document called Guidance for Obtaining Representative Laboratory Analytical Subsamples from Particulate Laboratory Samples, and the link is provided for you here. The subsampling guidance document ranks the subsampling methods from best, which is a sectorial splitter, to the worst, a simple grab sample collected from your original sample. This table can be used to evaluate subsampling possibilities in the field if needed. Many of these subsampling methods can be easily implemented in the field, others are more difficult, but a variety of potential methods is presented here. In this example, the incremental soil sample that was collected on the left has been spread out on a stainless steel tray and then has been systematically subsampled by building an incremental sample of the desired volume for analysis. This method is ranked number 3 in the subsampling method rankings of the referenced guidance document. The photograph on the left shows a riffle splitter, which was ranked at number 4, being used in the field to reduce subsample size. On the right, a cardboard box lined with aluminum foil has been used to create a 90-degree angle along which a sample can be spread into a 2-dimensional slab cake that can then be subsampled by alternate shoveling, which was ranked number 5. Each of these methods and the method on the previous slide provides a systematic method of collecting a subsample that is representative of the larger sample that is then ready for ex situ analysis based on the selected tool in the field. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. Now let's discuss how we evaluate the data that's been collected using these tools as part of our dynamic work strategy to make sure that we're evaluating data in real time and making the necessary adjustments to our overall strategy as needed. Proper data management and analysis is critical to any successful HRSC sampling effort. HRSC often generates very large data sets which require a pre-designed strategy for effective management, analysis, and communications. For field efforts using a dynamic work strategy data collection approach, newly collected data are ideally processed in real time. Following data quality assessment, the data are stored electronically and then evaluated spatially to refine the conceptual site model and to support the dynamic selection of additional sampling locations. Data must be collected at sufficient density to ensure comprehensive analysis of data trends at the scale of resolution appropriate to address site heterogeneities. Data may be collected in multiple formats, whether it's electronic, handwritten logs, etc., and all of that data has to be maintained to ensure that data integrity is maintained throughout. All data should be geolocated as possible, and we must evaluate the data in as close to real time as possible to determine if modifications are necessary to our dynamic work strategy. Depending upon the data quality objectives of the sampling effort, a key measure of the effectiveness of field analysis methods may be to establish a correlation between the field measurement data and data obtained from a fixed laboratory for the same samples. Paired data can be quickly evaluated by a regression analysis to determine the strength of the association between the data. In this example, 50 samples of paired data have been evaluated. The regression analysis shows a correlation with an R-squared of 0.98. That's near perfect analysis and is about as good as we're going to get with environmental data. Another thing that we can do to evaluate our data is to collect multiple readings of the same sample. When using field methods such as an XRF, colorimetric methods, collecting multiple readings of the same sample allows us to measure and quantify within sample variability using the method of analysis that we've selected. We can determine whether within sample has been adequately controlled by our sampling and analysis methods, and we can make changes as needed in real time using our dynamic work strategy to seek other methods of data collection if needed, depending on our data quality objectives. When collecting incremental samples, we typically do this in triplicate so that between sample variance can be quantified. This is a measure of whether the samples are producing a reproducible estimate of the mean concentration in the decision unit and whether the sample collection processing and analytical methods adequately control for heterogeneity. The relative standard deviation, or the coefficient of variation, is calculated as a measure of variance. Relative standard deviation is a quantification tool that evaluates precision but not accuracy. So we have to think about what an unacceptable RSD might mean for the project. A low relative standard deviation generally means that our heterogeneity in our soil has been adequately controlled through sampling and analysis, and that we can rely on the data, that the data are reproducible. High relative standard deviation may indicate that our data are not very precise, that there's some underlying heterogeneity, which may tell us all that we need to know. However, if we're looking for reproducible estimates of the mean concentration, we may need to consider areas where error may have been introduced either in the sampling or in the analysis of our samples so that we can adjust our dynamic work strategy to get more precise data. Some potential sources of error are listed here that we can consider for why we may have very high variability within our samples. It could be anything from the number of increments to the DU size and shape that we selected, or it could be that our field processing or lab processing was inadequate, that we have subsampled improperly, that our extraction or digestion methods introduced some error, or that our analysis was the source of the error. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. Let's look at two short case studies that highlight some of the things that we've been talking about today. At this site, low-density sampling collected through traditional means and sent to a lab for analysis was extrapolated to produce the concentration gradients below. The concentration gradients that are orange and red are the highest concentrations. The contaminant of interest, PCBs, has both relatively high analytical costs and, if determined to meet the regulatory designation of hazardous waste determined by its concentration, it can have disposal costs up to 300% higher than the soil contaminated with lower concentrations. An HRSC approach was used to collect high-density samples that could be generated in the field and used to refine the soil disposal disposition. Samples were collected at 20-foot by 20-foot grid at several depths to determine the nature and extent of contamination. Vertical samples were collected at 6-inch intervals. A dynamic work strategy was used to determine the horizontal and vertical extent of samples that needed to be analyzed in the field. Samples were analyzed in the field using a commercial electrochemical field analysis method. Correlation of the field samples with lab samples demonstrated that the results met the data quality objectives. Sample results using the HRSC sample and analysis methods were used to refine the estimates of the needed soil excavation. Excavation extent was confirmed with lab samples. At another site with PCB contaminated soils, incremental sampling techniques were used to develop a refined estimate for soil disposal. A test pit showed that soil beneath a parking lot slab was contaminated with visibly contaminated PCB containing oil. In this case, the site was divided into 11 sampling units. A decision was going to be made about the soil underneath the entire slab, but each sampling unit was going to provide additional information that would inform that overall decision for all of the soil. 30 increment samples were collected in each sample unit, and triplicates were collected from 2 of the sampling units. The sampled areas had increment locations marked with paint where each increment would be collected. A total of 450 total increments, or holes in the ground, were collected throughout this space. The skilled DPT operator on the site produced a core every 3 minutes. Of course, the paved area facilitated efficient sampling, but his ability was something to see. The handout version of this PowerPoint presentation includes a video that, again, I can't show and record over for today's purposes, but check that out if you can. He was producing these cores so quickly, and they needed to be processed by the field staff so quickly that they had to ask him to stop talking to them so that they could keep up with his progress. Measuring the depth of the visibly contaminated soil intervals that are marked with survey flags reading top and bottom allowed the team to develop a very precise estimate of the contaminated soil volumes that would need disposal. In the field, and it doesn't really show up as well in the photograph, there was a very distinct boundary that could be marked in each sample that showed that visibly contaminated area, and they were able to take a very precise measurement with 480 holes in the ground. They knew exactly how much of this material they would have that would require disposal. So these are the results in milligrams per kilogram of the PCBs, total PCBs, across the different sampling units. We can see that we have elevated concentrations throughout. These are all going to require some action. These were sent off to the lab for analysis, not for field analysis. But we were able to look at the triplicate samples and see how they performed. And using our calculation, understanding the mean and the standard deviation, we're able to calculate a relative standard deviation 12 and 26. Our RSD interpretation guide shows that's good precision. We're getting reproducible data that are high quality and we can make decisions with. So again, our incremental sampling data reduced some of the inherent heterogeneity. Our incremental sampling techniques reduced the inherent heterogeneity of PCBs and soils. Our high resolution of sampling allowed the project team to quantify very precisely how much of the soil needed disposal for estimation purposes. I'm going to be talking about how we collect those soil samples in the field, the analysis of samples, and as importantly, the field processing that may need to be done to make sure that you get quality results. Talk a little bit about how we evaluate the data to make sure that it meets our data quality objectives, and I'll end with a few short case studies kind of illustrating some of those points. And with that, we'll conclude our overview of HRSC tools and techniques for sampling soils. Thank you very much for this opportunity to speak with you today. And if you have any questions, we can answer some of those on the Q&A session coming up, or you can reach out to me via the contact information here. Thanks so much for your time.
OK， 我们谢谢 Tim 啊，他为我们带来非常精彩的1个小时的啊，包括从土壤采样，我们说的抓样混样，跟他介绍的这种累加式的这种可靠度比较高的，可以了解整个场址的这个平均浓度的这种规划的方法啊，还有各种的筛测工具。然后他刚刚讲到几个重点，就是样品的前处理啊，到底相关的规定是什么？你的目的是什么？在现场做还是回到实验室做？啊，其实我们以前在做农地的时候，我们是在现场做了很多的前处理，所以现场就可以及时知道它的一些重金属浓度的变化啊，就看你的目的是什么。那另外就是说，每一种样品的筛测要做几次，因为土壤毕竟它的变异性比较大，然后土壤污染如果是里面是有含废弃物颗粒的在里面的话，你筛出来数据那个变化也是非常的大，所以多筛几次可以确保你这个数据的可靠性哦。好，那因为时间的关系啊，我们下一场是由一样是美国环保署的第4分区的资深水文地质师啊，叫做 Ben Benkowski 啊，那他也是超过20年的相关的经验哦。那他也是一样，在进入美国环保署前，也在顾问公司有做过相关的工作，然后还有做过石油探勘的工作啊。那他今天他要跟我们分享的是有关于地下水调查的一些现场的一些即时的筛测技术啊。那他整个简报里面、影片里面，他会从整个技术的资料库，在美国有很多的网站上面，他们都有啊，大家可以去参考。然后整个跟地质相关的特性，你要用什么样的采样的方法，然后你各式的现场的这种筛测的工具，哦，那还有比如说再来就是说你得到的数据你怎么去判断？那我这边举个例子啊，其实我们在某个场址在台湾，我们发现其实在同一个含水层里面，反而是浅层的地下水的三氯乙烯的浓度比较高，深层的反而比较低。那这到底发生了什么样的问题？因为大家也知道，三氯乙烯它是比水重嘛，照理说一般认知说比较深层应该是浓度会比较高一点，结果刚好事实是相反哦。所以这个时候可能就要去怀疑说，是不是它的土壤里面，在浅层的土壤里面，其实还有一些污染物在这个土壤里面。好，那接下来我想我们就直接我们放第 第二段的课程。OK。
Hello, I'm Ben Benkowski, a hydrogeologist with EPA in Atlanta, and I'm glad to be participating in this training event on high-resolution site characterization. The module I'm going to present on is the on-site screening tools and methods, and this segment's supposed to last about an hour. Got lots of slides, so let's get to it. So starting off, we work for similar organizations. The US EPA and the Environmental Protection Administration of Taiwan both have laws passed about 10 years apart that require the investigation of the nature and extent of the soil and groundwater pollution at our sites. But we have a legal duty to investigate this contamination. I think that as environmental professionals, it is our duty to develop an understanding of the site using cost and time efficient methods that produce defensible data. So with that, this presentation will cover high resolution screening tools and method that will aid in making efficient decisions about site conditions and remedial actions. So these are the modules that, these are the main topics that we'll go through in the course of this presentation. Some technical resources, a variety of tools, and since I started out with a fairly large presentation, there are extra slides after the end of this, I think, hour-long presentation that I encourage you to take a look at later, because they just didn't make the cut for the 1 hour, but they're all still good information. So the first one that I think is a technical resource for folks anywhere in the world, really, are at our EPA's Clue In website. So this is technical information about innovative treatment and characterization technologies. So you can see all these blue boxes across the middle of the screen here. Those all have pull-down menus, and you can talk about, you can find out about all sorts of those particular contaminants or the strategies that we've got going or the various training events. So I encourage you to go into this website. The second one here is actually, you say it as CERTIP and ESTCP. These are government-funded environmental research programs. Seems to be mostly run by the Department of Defense with participation from the EPA and the Department of Energy. And they run full-fledged research projects. There are currently 250 plus active research projects on their website and on nearly 500 completed research projects. So that's a tremendous resource of high quality research that's available for you to apply to your particular situation, maybe. And also to help understand certain concepts, they've developed what's called this EnviroWiki, developed by the same people, but has really high quality articles written by invited experts, and I know there's another link for you to pursue. So there's a third organization called the Interstate Technology and Regulatory Council, ITRC. And this is not really directly a government-run organization, but run more by the states with participation from public and private sectors in all 50 of our states and the District of Columbia. So they actually have 52 different topics for the documents that they have produced that are available here at their website. For example, there are these pull-down menus that you can check out about the geology or the chemistry, bedrock or unconsolidated environments. I think one of the things we're going to talk about maybe in a different case study or maybe later in this presentation, is about their fractured rock tools. So just as an example, this is just the first item from their website spreadsheet on ground penetrating radar. You click on that and it gives you the description of the technology, the data quality and applicability and advantages, plus the limitations and difficulty. And for this subject, there are 10 references that you can pull up and learn about ground penetrating radar. And I think there are nearly 100 of these when you look at them on the website. So the other one to look at is provided by the USGS. So the U.S. Geological Survey is very similar in structure and mission areas as the Central Geologic Survey for Taiwan. We both are interested in understanding the geology of our particular areas and how that applies to resources that are available, natural conditions, the hydrology, a very broad range of topics. Both of us are fortunate to have a government-run organization about the geologic resources in our countries. So they actually have, in this particular thing, a fractured rock toolbox, like that one from the ITRC, where you go in and look at it, and it will tell you the various tools and ideas to use when you're looking at, well, in this case, it's just fractured rock. But they also go and do field investigations. I've used them on sites in North Carolina to run geophysical logging in our fractured bedrock sites. Top quality, top-notch organization. And I recommend you browsing their website. So this is their fractured rock tool. You go in here and you identify the various parameters that you have about your site, your goals, and then it will give you some suggestions about what has the best applicability, what's a relative cost. No sense having to figure this stuff out yourself when someone else has spent considerable time and effort to make it easier. So I recommend all 4 of those resources to delve into topics that are, we've only got an hour. We got lots of slides to get through, but those other these 4 resources will be great for your future review. So the first talk about the individual tools will be for shallow, unconsolidated environments, starting with soil coring. So, essential information that you should receive from cores is both geologic and hydrogeologic features, a variety of properties depending on what your interests are at the site, understanding about essentially the permeability so you can understand the contaminant mass distributions, and then also those same contaminant concentrations can give you some gradients, and understanding then once you get those 4 basic understandings, you can come up with some understanding of the effectiveness of how the various remedial technologies can work on, say, of clay-rich area that has a lot of VOCs, or a very sandy zone that has a lot of creosote in it, or any number of things. But coring is really one of the basic steps. My first job was working in the field, actually seeing cores that came out of the ground, and there's just something about physically seeing the rocks that you're investigating. So things that you need in a coring tool, it'd be really great if you could get 100% recovery. You got to be able to know exactly what depth it's from, which requires coordination with your drillers, so that you really get an understanding of how deep that sample is from, because you're going to need to correlate that with the ones from other parts. Plus, you need to be specific about the depth to more than the foot, hopefully to the 100th of a foot, because sometimes that makes a difference. You'd like the samples to have a minimum disruption of the, as you bring them to the surface, and retaining the pore fluid, so you could then actually, if you want to, sample them and then send that off for analysis. Should be as the one you see at the surface, the samples you see at the surface should be as close to subsurface conditions as possible. And no, I won't be reading all the slides. Here's a photograph of a core cut in half. You can see these various beds, some very fine grain. I mean, this is a matter of, these are inches and centimeters here at the bottom. So you can really see, like in this case, you can see this little offset in the bed. That permeability difference might make a difference in how the NAPL or the contamination moves within an area. So this level of detail can be important, because it all moves from pore throat to pore throat, from between the sand grains. So it's important to have high quality data. Here in this particular case, in the middle of this fairly thick clay, I believe that's centimeters at the top, you'll see that there is a little tiny sand zone, and that sand zone was treated with a dye that turns red when there's DNAPL present. So in the middle of that big fat clay is a little zone of DNAPL. So it's you would have missed this if you hadn't had a continuous core. So how can you, what are the methods you normally use to get cores? For deeper zones, sonic seems to be the best, because it's, for unconsolidated zones, I've collected sonic cores down to 200 feet before. Rotary has more a thing called the split spoons, and it's, the cores are in a little better shape, but sometimes the production is a little slower than with sonic. But sometimes the conditions are that you need to use the rotary, because oftentimes you have to use water with the sonic, and that can dilute out in your samples, could dilute out the fluids in the core if you want to take some representative samples. And then for more shallow and less consolidated or less indurated zones, you can use a direct push rig to just push the core barrels down into the ground. These are those split spoons that I spoke of earlier. This is with the geoprobe. This is also with a Shelby tube. That's usually done with the rotary methods. These are all single rods that are just pushed in the ground. The dual coring, I think, is probably a better way to go these days. There are, you put in an outer casing which stays in place, and then the core barrel is tripped in and out of the hole. It's better because you get a a more intact core and you have less contamination from sloughing in the hole. You get better recoveries. In this case, this guy is using a special tool to split the plastic casing around the outside of the core, and you can see you get 100% recovery with this. So you can also, the Sonic rig also does these dual core process here, because there is a big tool that runs the casing down to a certain depth, and then the inner barrel vibrates this core, the inner barrel, down to the 10-foot zone. Usually it's about 10 feet. In this case, they got back 8.5 feet of core. But it was able to give continuous cores for, down to 315 feet deep, which is really, that's a lot of characterization, that you have essentially a complete record of the sediments from when you start to when you finish. So problems with some of because you're using this vibrating equipment to advance the casing, sometimes it just disturbs the sediments. If the sediments have a very high amount of sand, it's more susceptible to disruption. If the formations are too dry, then you have to use some water in order to advance the tools, keep things from sticking, and that can dilute any of the water, any of the fluids in the core, and you'll get reduced concentrations for any VOC samples that you collect. And it can be highly disturbed. It doesn't have to be. I've seen cases where it's come out just fine. Maybe you'll lose a foot or so, but maybe on the big scale of your investigation, having a 90% recovery would be okay, because you'll get very good data off of the samples that you do get. You can get grain size analysis, you can see sedimentary structures, you can see siltier zones that might control the movement of NAPL. But in general, cores are some of the best information you can get to actually see what's in the subsurface. So this is an example where the water usage really diluted out the TCE that was in that particular zone. This is the groundwater samples later, once the well was installed, but the water sample collected from the pore water of the Sonic core is about 2 orders of magnitude less than the groundwater samples from the well installed in the area. So again, it really becomes more of a screening tool that when compared to a monitoring well, a permanent monitoring well. So the next subsection is about hydraulic and chemistry profiling. So the first tool to talk about is a cone penetrometer. So the cone penetrometer will give you a continuous stratigraphic or lithographic profiling. It can be part of a tool system that's put in place. This needs to go first in the hole because the pressure on the tip is compared to the friction on the sleeve on the side of it. And that's how it makes its determination of the lithologies. So it generates data in real time. It's been used in Taiwan. Here's the paper which talks about the liquefaction from an earthquake. But it is a static push, but you get continuous high quality data. Here's an example of the truck that they come in, and these usually have a hydraulic rig inside this truck, but then it's all contained out of the weather. And this is two examples of the cone penetrometer. This is the tip, that's the sleeve. These are the two strain gauges that record the forces from those two. And this is usually a water porous, so you can get the hydraulic pressures, the water, the pore pressures at depth. So in this case, you can see the sleeve stress is plotted across from the tip stress or pressure in PSI. That's converted to a ratio, and then you can correlate that with the soil behavior terminology. So this readout here can then give you the lithologies that you get in the subsurface from pushing this tool through those zones. And the pore pressure pops up when you're in this clay zone here, and you can get that reading as well. So soil behavior type, excuse me, I had that wrong, but you can see that the sleeve friction on the x-axis and the tip pressure on the y-axis, and those two values plot out to a sandy zone or gravelly zone, a very stiff clay. Anyway, it's a very useful tool, very basic. It was developed by the Dutch, which is not surprising given how much land recovery they try to perform in the Netherlands. But that's where it was developed, I think, shortly after World War II. Very good for lithologies. So there's a couple of versions of the hydraulic profiling tool. In this case, this is without sampling, but it's a continuous profile. You can describe the hydrostratigraphy based upon water that is pushed into the formation, and you run it off of a direct push rig as well. So here's the example of the tool. This is the zone little screen here where water is pumped into the formation, and there are some gauges that understand how much water is going in, what the pressure is. So this is the setup for the equipment, the computer, the controller for the pump, and then the pump itself. And what you get is, this is the pressure of essentially the water pressure of the water being pumped into the formation. This is the flow rate. This is the corrected pressure, processed somehow afterwards. And then from this information, you can get the estimated hydraulic conductivity on this curve here. And you can see, this is the top of the water table, and then the hydrostatic pressure increases as you go with depth. But then you can see this zone here that's got a fairly high hydraulic conductivity, and these little other zones here, then you can match this up with the electrical conductivity and help you understand the hydrogeology of this with this tool. Again, this is the cone penetrometer data, the pressure data, and the electrical conductivity, and you can see this, like this zone right here has low electrical conductivity, low pressure, and a low friction ratio. So this is probably a sand unit from this 10 to 13-foot interval here. Again, it's the laying out logs in a in a horizontal fashion, so you can make a little correlation between the three of them, or however many you happen to have. So this is the same basic tool, but then with a water sampler associated with it. So this is a schematic of the groundwater sampling version of the hydraulic profiling tool. As you push the tool in the ground, it's injecting water at 400 milliliters per minute, advancing at about 2 centimeters a second. If you see a zone that you're interested in sampling, you're then able to stop the probe, purge the system of the water that was injected, and then collect a sample that is then pumped with this bladder pump up to the surface and into your sample collection, into your sample bottle. This is a separate one here where there's a direct push tool that you push into the ground, and then it exposes a screen that you can then just leave there. I believe they're disposable. No, removed following the collection of each sample. But then that gives you a screen interval for collecting a sample with a peristaltic pump. So there's a different system called a Waterloo profiler that's got, like many of these systems, tools that go down the hole, lab equipment in the trailer, and computer equipment to store the data that are collected from the process. So again, there's the point and the samplers. This is the way it was, 25 years ago. But now the more advanced tool is improved with screens, and I'm sure based on their feedback through the years. This is a schematic where you actually push it down, and then you're able to adjust the tool from the surface and then collect groundwater samples. I mean, this is all very, inch by inch, centimeter by centimeter, if you want to characterize to that level of detail. This gives you that high resolution data by using this kind of equipment. This is the schematic of how it works, where you have a compressed nitrogen that comes down, works as part of the profiler, and then you can switch it to sample, and it draws the fluids out, and you put them into these bottles, and you can actually then, I think, do these fill parameters, which are often so very important to understanding the information about the characteristics of your, is it low dissolved oxygen? Is it a negative oxidation reduction potential? All this is really important for understanding your aquifer characteristics and what's the state of your contamination. And then you can use the water samples that are collected with their on-site lab. This is an example of their cross-section where the chlorobenzene concentrations are in the red, but the hydraulic conductivity zones are in this brown line that pops out through here and here. So this is an example of the data you'd collect, and then a few of those in a row gives you a stratigraphic interpretation, as well as concentration data for your understanding of the extent of contamination. So this is, again, a couple of logs set across from each other. the membrane interface probe data with the photoionization detector, the index of hydraulic conductivity from the Waterloo profiler, and then the concentration of those of TCE and 111 trichloroethane. You see they're pretty high in this higher conductivity zone, and still pretty high in this lower conductivity zone. But then there's less of it as you go further down the hole, and as the formation probably fines into a finer grain, a fining downward sequence. This is an example of using these multiple tools to give you foot by foot or better resolution for your contaminant distribution. So it's really one of the things that's been developed in the last 5 years or so are these very high quality field gas chromatographs. This is not a commercial endorsement, but it saves a lot of time if you can actually get high quality data in the field while you're doing your work. This is one model called the Frog 5000. And if you look at it, from the front side, it sort of looks like a frog sitting there. It's very lightweight, and you can use it. I've used it on my projects, and you get high quality data in a short amount of time. Another tool is this HAPsite, and it's the same. It's a different tool, but it has the same outcome from our interest in that you can get high quality analytical data in the field that's used for real-time decisions about, are we finished going deeper? Do we have it delineated in this particular direction? I've had folks that use this on sites that I'm involved with. So yes, both of these I can recommend as a way to get high quality information to make some decisions while your crews are in the field, and you can then have them keep working in a particular direction. And you can say with confidence what's going on. So these are some qualitative tools for discussion here. So this is the membrane interface probe, which I talked of earlier. So there's this Teflon membrane that warms up, and a carrier gas. As the membrane warms up, the VOCs in the groundwater are then transmitted through the membrane and into a carrier gas, which is taken up to the surface and first through a photoionization detector, which is just a general all-around total VOCs. And then you could have any of these other three, which are more specific and give you better readings, better specificity. You can actually be a little more specific in your results. And then this electrical conductivity, that usually correlates to your lithologies. So, between the two, you can get a pretty good idea of what's at a screening level, what's going on at your site. This is what that setup looks like. Pretty similar to others in that there's a direct push rig. There's a truck that has this equipment inside of it. This is the tool. That's the little window that warms up and that's being pushed in the ground by this operator. And this is the readout that you get from a particular boring log. Here's a little better closer view of that same boring log. So you can see the electrical conductivity on this scale doesn't really show a lot. So the PID, photoionization detection, shows this amount of deflection, but the electron capture device, the ECD, shows a much bigger response. And then the electrical conductivity is a smaller number. But you can see this is the rate of penetration. It goes in and it stops, goes in and it stops. You could do this every foot or so if you had the time, or if you had a particular zone where you needed higher quality, greater data density. But this was one of the first one of these subsurface tools that I ever saw at work, high resolution tools at the Kennedy Space Center in Florida. And once we started doing this work, we pushed the tool down in the subsurface, and there were these little silt layers that showed up on the electrical conductivity readings. And we stopped right at the top of those zones, ran the MIP here, and got these big hits on the PID. We were able to find a whole series of these little silt zones with high concentration zones right on top of the silt. That investigation with this tool led to a complete change in the approach at that particular site. So that was 20 years ago, and I still think it's a great tool. So you can certainly get vertically continuous data. You can do a couple hundred feet a day. You need to worry about things that you might cause you not to be able to get to depth. You get a rocky condition, you're not going to get good penetration, and there can be some lack of resolution of the data, because there is some drag down, especially if you have a high contamination zone. Remember, it's screening level data. It's not like the same as a permanent monitoring well. The other thing is that the compounds that are heated, they volatilize at different rates. So then they come up to the analytical equipment at different times, not unlike a little chromatogram. So if you have a zone with naphthalene, it's going to get there a lot slower than a zone with PCE in it. And you need to know your site and take that into account in the rate that you allow, the time that you allow between where you push and activate the sensors. So this is an example of that, where the actual soils data here in the multicolors are compared to these other zones, and where the membrane interface probe is a couple of meters off from comparisons to the actual soil analytical data. In the grand scheme of things, a couple of meters won't make or break a project, but it does give you an understanding of that there's a hot spot down there, even though it might actually be a meter or so in a different direction. You'll come back through and take some soil samples and nail it down, or take some groundwater samples and nail it down. So this company in North Dakota developed a thing called a laser-induced fluorescence tool. It works for aromatic compounds. It detects NAPLs. Again, it's a direct push tool. And when you push it through, depending on the compound, you get a different reflectance. You get a reflectance at a different wavelength. So whether or not you're pushing through what might be petroleum as an L-NAPL or a D-NAPL of creosote, You need to have a different tool and you'll get a different response, but all that is understandable with these particular tools. There's the UVOST that works on, mostly petroleum products. The Targost, which works on creosote, and the rapid optical screening, which works on fuels and oils. And their website's got a lot more of this information on it, but just understand that, once again, there's a tool. It goes on a direct push rig, and it sends the information back to the trailer, or in this case, the shipping container that has the computer and the control equipment, and then this computer over here, which actually saves the information from it. So this is a readout of the log. So you should understand that when these tools get pushed in the ground, there is a laser that is projected out into the formation. And NAPLs, L-NAPLs or D-NAPLs, will fluoresce at a certain frequency. So they shine this laser with a very specific wavelength out into the formation. Then it records the wavelength of the reflected light that comes back, of the induced fluorescent light that comes back to the sensor. So these wavelengths, this is very specific about the different types of compounds. Understanding them is almost as much of an art as it is a science. I highly recommend that you go to this website down here and learn their instructions on how to interpret these. But you can see, you get these really strong indications of where the NAPL is, how it's distributed through this zone here. Especially if you have some other information in the subsurface, you can match this and really learn where your source areas are. They have another relatively new tool, which again looks on the laser-induced fluorescence and the wavelength of that light that's induced. In this case, there is an injection of a fluorescing hydrophobic dye. As the tool is pushed into the ground, this dye is continuously ejecting a very small amount, and when it runs into one of these NAPL zones, the dye adheres to it and then is available for the fluorescence. Once you keep pushing this down, this little window, this little sapphire window, will come across from this zone here. The laser will hit the dye, it will fluoresce, and then the data will then go back up to the equipment in the trailer. And so you can get very detailed information. This is the general log, like how it was on one of the previous slides, but you can process the signal to just only show the DNAPL signals. And so this is less than resolution, better than 1/10 of a foot or better than 3 centimeters. But you can see this around this 34-foot zone. This is an area that you'll want to concern about regarding source area remediation later. And even down here, there's this one little, 3 centimeter zone at 67 feet. Probably this little zone right here. Now, is that going to be a big enough problem to cause you a very long-term groundwater problem? You'll have to understand. You'll have to sort of learn about that and see what the dissolve phase concentrations are in that area. But it's but for the resolution, it's a a spectacularly useful tool for source area identification. That's the dye, LIF is what it's called, because the dye is injected and it's laser-induced fluorescence, and you have a level of detection around 1% or a little less of DNAPL pore saturation. Now, they say here that you can get maybe 400 feet per day, and if you did shake tests with oil red O, which is the hydrophobic dye that turns red, that's equivalent to over 12,000 shake tests. You could never do that in a day, certainly. But you get, what's that, half a centimeter spacing. That's very high resolution data. I don't know if this is available overseas, but Randy St. Germain, the man who founded and runs the company, is very amenable for technical discussions, and I found him a useful partner in trying to understand things. So, tools for fractured bedrock. We've got some stuff that we're going to cover here, but also some of this is covered in a case study in the other methods part of the schedule on day 2, where I talk about an investigation that I did in North Carolina that it sort of helped me understand the process that I think gives you the best understanding in fractured bedrock. So in general, if you have a source zone where there's DNAPL into a fractured rock zone, it goes down here into these fractures. Some of the DNAPL sorbs into the rock matrix, some of it turns into a dissolve phase plume, and really there's no good way of knowing from the surface where your contamination is. Basically, you need to drill some holes and run some logs down some borehole geophysics and sampling equipment down the holes in a certain sequence before you can really understand which direction your contamination is going and what's the nature of this fractured rock aquifer, if it's metamorphic or if it's a sedimentary like a fractured limestone. It's generally the most difficult zone that we have to deal with in our profession. So this is actually a borehole tool matrix. The ones I've highlighted in yellow are the ones that I prefer. But you can see the various bits of the types of information available on the left and the tools that you can then use to understand that information, and then the secondary use. And anyway, I'll leave this for you to study later as you try to map out your next fractured rock investigation. So there are 4 or 5 technologies here about multi-level systems for fractured rock or other settings. The simplest is just a nested well where you have one borehole and a couple of different pieces of PVC casing set at different depth with the right amount of sand pack and grout between them. But these others are a little more complicated. So for the Waterloo system, it's a series of packers and casings and sampling ports that you install at depth at specific intervals that you may have identified previously with your investigation techniques. The multi-level system, it actually comes as a PVC, not PVC, but a flexible plastic tubing, a polyethylene, that's divided into separate segments that run the whole length of the tubing. I've used them more in coastal plain settings than I have in fractured rock intervals. But you basically go down to a certain zone, cut a hole in the side of the pipe, wrap it with some screen, and then that becomes your sample depth. And all of that is run off one single, about 2-inch piece of polyethylene tubing. So here's somebody putting one of these together. You put some centralizers on it. It's all laid out in a row here. There it is being run into the well. And in the end, you have these little samplers that go down into these 6 different zones. And I think maybe the 7th is possible. But that gives you a lot of information out of one borehole. The West Bay system, again, is a series of packers and samplers and have various ways to control this from the surface, but you can then set this as a permanent well to sample individual intervals. The flute system is a flexible liner. That's what the FL stands for. It's, this goes into a hole, into the borehole, and you need to specify the depth that you want the sampling ports made into this fabric. It's, but it allows you to then pump from this, say from this particular interval here, through connecting up the plumbing up at the surface. So here's an example of it going into the ground, into the borehole, and you attach it to the top of the well, and then you start putting some water on the inside of the tubing, and the material just flows into the borehole. But because it can go in at a specific rate, there's an interesting development here, is that as the tubing goes, as a flexible liner goes into the bedrock, it has to displace the water that's in these fractures. The more transmissive the fracture is, the quicker the liner goes past that point. So you can record the velocity of the liner going into the hole and correlate that with the transmissivity of these individual flow zones, individual fracture zones rather. So, this is a very high transmissive zone. This might be where most of your groundwater is coming through, but this may also have the same levels of contamination, but just not nearly as transmissive. So it's an interesting idea. One of the things you can also do with it is you put this this felt activated carbon on the sides, and it wicks dissolved phase materials into it. Then you can cut those out and send those off for analysis. Or you can do that with NAPL and dissolved phase, and then you can send it off for analysis. Or one of the other uses of this is if you have a borehole that you need to seal, but you haven't had a chance to design the well to go in there, then you can use this to go into the hole and seal off the formation so you don't get cross-contamination. So for some non-depth specific activities, you can use passive diffusion bags. It's fairly simple. You just drop it in the well to a certain depth, and it relies upon maybe a 4-week time period for the water that you put in the bag to come into equilibrium with the water that's moving through the well. So it doesn't generate any investigative derived waste when that's one of its big advantages. And it's a fairly labor simple kind of a process. The other thing is these passive grab samplers. This is a thing that you can activate by pulling a cord, and it pops open a sample bottle that then fills and then shuts. And this is actually one that goes down to some depth, and then the water, when you pull it up, it fills the hydro sleeve fills with water. It's kind of like a one-time bailer for collecting water from a specific depth. So for groundwater surface water zones, it's one of the things I've learned in the last 10 years or so, that all the groundwater usually goes to a discharge to a creek someplace or to a big river. So understanding this transition from the groundwater to the surface water is becoming an avenue where it sort of expands your hydrogeology notion. And it's useful for both screening and you can get very detailed levels of understanding because you can work on really short intervals for your sampling. Using this is just a hand probe. It's about 1 meter long or almost 2 meters long, and you have little slots in it, and you push it to a certain depth, and then you can put some tubing down this probe and collect a water sample from the transition zone in the sediments of adjacent to a lake or in a creek. But it's a really simple way to get depth-specific data, and it really all depends on how much further down you push it. If you wanted to get a 20, 40, 60, 80 centimeter sample, you certainly can. So this is a pretty interesting thing, an infrared camera that's using thermal imaging. The technology has really come a long ways. It's handheld. You can mix videos, take still photographs. I used it, again, provided by the U.S. Geological Survey at this site in North Carolina. And when this orange stripe here is this vine that comes across here, and you can see the cold water coming out of this very specific location. Well, when you look at it in visible spectrum, there's a crack right there where the cold groundwater is actually discharging from a point discharge, and you can see a 4 degrees difference between the surface water and the groundwater. Next slide is actually taken. This next slide is actually taken in the winter time, more of a diffuse flow, but again, you can really see where you should take your sample if you want to understand the concentration as the groundwater discharges and then mixes into the surface water, and then maybe take a sample, 5 meters downstream to see what the average concentration might be after the mixing zone. But it really allows you to pinpoint specifically where the groundwater is discharging. So a distributed temperature sensor, they're fiber optic cables that are laid out, could be, great distances, up to 30 meters in length. Anyway, there's quite a number of configurations. You can get a spatial resolution of about 1 meter, but the thermal differential is down to a 100th of a degree of Celsius. And because it's run basically with a laser tool in a fiber optic cable, you can get very high quality, high resolution data. So this is some of these cables being laid out before they're going to be deployed out in this lake here. I think this might actually be Lake Michigan, but there's a USGS story about that. And you should, if you want to really delve into the science of how these things work, there's a great article on Wikipedia for this. Look it up. I won't butcher it by saying it here. But you can get really good detail, but you can see in the stream, like in this particular situation, in a stream, you can see the cold water discharging at certain specific places here where the groundwater is discharging, and then out into the pond where the spring is. But then these are places that you'd want to go back to sample for the groundwater discharging. But you can see the temperature is very high resolution over a matter of meters. Here's an example of some of it done in the field along the length of a creek, some older data, and then this connectivity survey data. So anyway, I believe that's the end of my presentation. There are indeed quite a number of other slides after this, which I encourage you to take a look at later. But I'll close by saying, 谢谢。
谢谢。好，我们再谢谢 Ben 啊，带来给我们很丰富的内容啊。那其实这一个简报、这个影片主要讲了很多现地的或者现场的我们可以使用的调查的工具，所以大家可以依照你的调查目的跟污染物的特性去使用相关的调查的技术。那有一些地下水的采样的方法在台湾可能还不多见，那这个当然跟我们台湾的采样的相关的规定可能会有关。那有一些是我们在整治过程中我们自己可以做的，那就比较没有关系啊。所采出来的数据也可以我们自己来做参考。那我不知道高老师，你刚刚不知道你有没有什么要先跟我们分享，还是说等一下一起？还有吗？好，那我们就等一下。好，那因为刚好现在我们表定是我们中间休息到3点半，所以我们还是一样，我们到3点半，然后我们下面最后这2堂课，今天的，好，我们再来进行。OK， 谢谢。等一下还撑1个小时。对，等一下还有1个小时。半夜了，12或13个小时。讨论那个下午是2个哦，下午是2个，后来有没有改？那个是线上的。 来，我们现在是不是超过3点半了？我们大家来进来就位。等一下，下午最后2堂的课程就要开始了啊。好，那我们下午第3堂的课程，我们现在开始啊。那第3堂的课程也是由妹的啊，妹的她今天上午有讲了1堂课了。那她这堂课主要就是说，我们做完了这么多高解析度的调查工作，收集了那么多的数据以后，我们怎么去用在我们的整治的策略上面啊？怎么去做规划？然后怎么去做相关的评估工作？那第3堂跟第4堂课都是半个小时，然后这2堂结束以后，我们还是有请我们的老师们跟我们美国的专家们会来做一些讨论的工作啊。如果大家有什么问题的话，也可以在那个时候来提出。好，那我们就先来放第3堂的课程的影片。
Hello, this is Matthew Jefferson, and for this session, I'm going to be talking about application of high-resolution site characterization to remedial design, implementation, and optimization. And so it's easy to think of high-resolution site characterization as just something that you would do during the characterization phase or an investigation phase, but there's many implications in terms of thinking about what the technique or the tool has for design and construction. As an overview, we will be talking about 2 different media here, both groundwater and soils. And so for high-resolution site characterization for groundwater, we want to review over the high-resolution site characterization key concepts and talk a little bit about the influencing factors that govern our designs. For soils, incremental sampling designs, some of the key concepts are regarding the decision units and the conceptual site model, and we'll walk through a case study highlighting both uses of decision units and the conceptual site model. And then we'll talk a little bit and give a brief overview of the optimization and how optimization works and some lessons learned during the remedial design phase. So just to recap, high resolution addresses 2 critical issues. The first being the sample scale and data averaging, meaning that we're looking at measurements that must be made over a scale that is meaningful with respect to the variability of the quantity that's being measured. And the key word I focus upon is that variability. And so when I think about that, I want to understand what concentrations there are in a particular area that's out there. And what are the maximum concentrations? What are the hotspots that are out there? What are the vulnerabilities and sensitive populations or ecological considerations that I need to consider in order to gear my remedies so that it is addressing those sensitive populations that are out there? From a geologic standpoint and looking at the subsurface, I want to understand what the nuances are in the geology, so that I can understand what the preferential pathways are and what the remedial timeframe will ultimately look like when I design my remedy. The second piece of this is thinking about the coverage. And so I want to have enough measurements in the right locations. And when I look at sort of plume maps that are out there or contaminant distributions, it's easy to sort of get to think about those as 2-dimensional or planar surfaces. But in reality, really, we must consider both horizontal spacing and the vertical spacing, because the contamination is in a 3-dimensional space. And so what that means is that implies what we need to do, what we need to consider as far as what designs there are for our remedies. So from a design perspective, as an engineer, it's critical that I understand where exactly the contamination is. And so I'm going to revisit the high-resolution site characterization methodology in terms of investigation, because so much of that, of understanding where it is, affects what type of design and what remedy I ultimately choose. So if I'm going to look at this design here, if groundwater is moving from the left to the right, and I have a source that is here on this area here, I want to paint my transects that are perpendicular to the groundwater flow, and where I can get an idea of what the down gradient, up gradient, and down gradient areas are, and also get an understanding of what the subsurface looks like and understanding of the spacing in the vertical axis. So when I start getting information back from the field, I can get a lot of really good information about both the contaminant concentrations that happen in between each one of these transects, and also information regarding the geology that's below in the subsurface. And that tells me not only what type of concentrations that I'm dealing with, but also the flux or the contaminant flow as it passes through each one of these transects, going from the up gradient source to the down gradient area, and how I might design my remedy to tackle each one of these sections of the plume. So depending on the conceptual site model components that I'm dealing with, and also the site and some of the site issues that we worked out through our scoping process, I might choose something where I have a 3-part remedy, where I choose a very aggressive remedy up at the up gradient near the source area, and then something a little bit more passive towards the down gradient side, maybe where my receptors are, or where there may be an extraction well or a drinking water well is. And so, for example, from the information that I get from my subsurface, I may want to do some sort of excavation of the source area, so that I cut off the contamination from the source itself. And then I might want to follow it up with some soil vapor extraction and install specific wells in areas where the highest concentrations are within the subsurface here, and have that going up towards a treatment area, treatment system that's constructed here. In the middle part of the plume, I want to think about potentially some targeted pump and treat areas. And so when I'm thinking about like what type of extraction wells that I'm looking at, I want to design those extraction wells with the screens in the hottest part of the plume, where I can also get the most amount of contamination out of that particular area. So having that mass flux information is particularly critical here. On the back end of the plume, if I choose something like in situ bioremediation and maybe some recirculation techniques here, again, I want to know exactly where I want to target that, and then what type of concentrations I'm dealing with, right? And this all has to go to the performance standards, thinking about whether or not those, if I'm choosing some sort of bioremediation, whether or not that is successful, or I need to switch it off to something else. So I want to highlight the importance of vertical spacing here as we think about our groundwater design in itself. And so what I'm showing is 3 cross sections of the same area using 3 different techniques here, with the depth on the y-axis and horizontal spacing of on the x-axis. And we're using the transect method. So we've got our boreholes in each of the locations, and we're keeping them the same for each one of these vertical spacing considerations here. So the first one is typically a driller's type method here, where we're taking samples both at the shallow, medium, and deep areas. So the shallow being at this horizon, the medium here, and the deep here. And notice that I've got a concentration of about 100, and seems like I've got a little bit of a core that extends right here, another core that's in this location, and then another one that's off on our right-hand side here. And of particular concern, it looks like it goes even further off to the right, meaning I've got to do probably a little bit more investigation here. I may have some concerns off to the left too, because I don't have enough resolution on that side. So, but notice how that changes when I change the vertical spacing to 3 meters. And so now I actually have a better understanding of what this plume looks like. It's a better bound between each one of the horizontal transects, their horizontal spacing, and then I have a better understanding of what that 100 core looks like. I've got 2 locations that are here and here. Nothing off to the right-hand side. But if I push that even more towards a 1/4 meter vertical spacing, now I have a better idea again of what this core looks like. There's something that's off to the left here. There is something towards the middle here, and it extends off to more towards the right. And so I want to highlight a couple of things, and it looks like there's one that's up near the top here between these two boreholes here. I want to highlight a couple of things. Between these 2 images, notice that this one picked up, the top one picked up a plume off to this side, where the middle one did not, and then the one on the bottom did pick up that plume again, and that's just simply because of the happenstance between that borehole and what that spacing looked like. Another interesting find is that there is a clear core to this plume here, even higher concentrations than what I had between the other 2, where this is almost 100 times the magnitude. Notice that there's another little core that's out in the middle here. And so there's 3 things that I would like to consider here for design consideration. One is, do I have this plume bound? Do I need to go further off to the right or the left as far as my transects are concerned? Is that of concern? Because when I start to design my remedy, I want to make sure that I pinpoint exactly where my influences are for my remedy. The second consideration is thinking about the aggressiveness. Now, how aggressive do I want to treat this? Do I want to do some sort of active pump and treat? Do I want to do some sort of in situ remedy or bioremediation type of remedy that's out there? How aggressively and to what performance standards do I want to consider? And then finally, once I've chosen a particular remedy, where exactly do I want to target this? And so this yields quite a bit of information, but think of it also on the back end of it, of the cleanup. If my core, the plume core, is right there in the middle here, and I've missed that plume core because I thought the images looked more like this, then it's going to take a lot longer to achieve my remedial performance standards, and it's going to take a lot longer to clean this up. For our soil sampling, high-resolution site characterization, for our incremental sampling designs, what we want to consider is our decision unit designs. And so our decision units, of course, are an area of concern where we might have an exposure, might be an area that may have been a source area, it might be an area of a spill, or it might be something where a particular land use is of concern there. Those are all things that help us define what the boundaries there are for the decision unit. And think about the boundaries not only in the horizontal aspect, but also in the vertical aspect. So that's what's being highlighted here on the image in the yellow dotted lines here. And then we also have to focus upon those increments themselves. And the increment locations are the yellow X's that are on this image. And so ultimately our goal is to get to 1 to 3 kilograms. And so we need to think about the tools that we use to get us to that point so that we have even amounts of soil per increment over that entire area. And so the other thing that we want to consider is the number of increments. And usually we start off with a a minimum of 30 increments. But also know that we may have to increase the number of increments depending on our replicate data, and that the decision units are generally less than 2,000 square meters. And so we want to keep these decision units tight so that we can identify where those hotspots are and identify what type of variability so that we can make decisions on that area. And the driving force behind those decision units is the conceptual site model. That's also getting an understanding of what the land use would ultimately be, what are our objectives that are out there, and what potential flow paths or pathways is happening at our particular site. And another thing to consider is using real-time tools and integrating that with our design, because that gives us a good understanding of whether or not our designs are working. Did we design the decision unit too large? Did we accidentally capture too many sources within that decision unit? Because we're going to be piecing all that information together to refine our conceptual site model. So I'd like to highlight some of the design considerations in thinking about incremental sampling and our high-resolution site characterization with this example from a mining site that we had worked on. And so this is most of the mines and mills are all located from the left-hand side towards the middle. That's what this yellow area is showing. This is the bottom half of a canyon, and when there is flooding, water runs through off of this yellow area. This pink location here is where they have observed some tailings and other ore deposits that are from a resultant of all that historic mining. And there's some samples that they have taken from various locations. And so also to note, about 4 years ago, from the time of this recording, there was a massive flooding event. It covered this road here that I'm highlighting across here with all sorts of sands and different types of deposits from the canyon itself. And one of the major concerns was there contamination across there. So all these roads were covered in dirt, along with many of these residents that you can kind of see in this particular area had some flooding damage there. So this was a particular concern to see what the impact was. You can kind of see that there was some higher concentrations. Their action limit was around 80 parts per million here, and you notice that there's some concentrations that are in the thousands here. So they chose to use an incremental sampling design to see whether or not they needed to do some cleanup in this area, because you can see not only are there concentrations in the thousands, but there's also some concentrations that are in the single digits. So as far as our design, we wanted to mirror the flood pattern that we had observed, not only observed when we did a site walk, but also what the read counts were from the regulators that we had interviewed there. So starting off to the left-hand side, again, this is the area where most of the flooding started, so we had a source, what we considered a source area, and following the river down into this direction. And then from what we had understood, the flow had gone both across the road itself and down these channels and along the roadway. So we painted our decision units, which you see in the purple and blue boxes here highlighted in this slide, to reflect each one of those stages of there. We also wanted to get an understanding of what the impact was to the residential area here. And so we painted also these decision units as we would go across and see what kind of impacts before they got into the residential area here, both in this area and this area here. In addition, we were concerned also with the spoils or the areas that were bladed off as a resultant of clearing the streets. And so we had selected a decision unit back on this side to sample the embankment or whatever the spoils were as part of that. So interesting enough, we did our sampling design, and we found a lot of interesting things about our what the conceptual site model was. And so even though the same image, again, here's where the mouth of the canyon is, and here's the flow path, it turns out that most of it actually kind of ran down the street, but it never did do this larger jump across there. What we did notice was that there was actually a source area highlighted here in red as part of that decision unit, and a separate source area up here, along with a third source area back in this area over here. We had to make several adjustments to our decision units, partially because we could not get permission to go on this landowner's area here. So we had to adjust our decision units based on what type of exposures that were out there. So as a result of our sampling, we have a better idea of exactly what type of contamination that was out there and where the location, where the contamination or where those focus areas should be in terms of doing some sort of response there. So, but should note that there's several things that we've learned about that, some limitations that we had about some of the equipment that we used. And so, first of all, the sampling tools that we use a similar sampling tool as shown before, this alligator sampler. Those samplers were really easily damaged and could not retain those fine, dry soils at some of the locations. We were working in a desert location, and so it was difficult to sometimes retain that a sample. So we're looking into other options, either a pogo sampler or just trying to get a better redesign of the alligators so they don't get beat up as frequently. Another thing that we observed was that both using incremental sampling and X-ray fluorescence was very, very effective. So not only did it give us a chance to verify our designs that were out there, it gave us a really quick assessment what contamination, so that we could hone in to the specific areas that were of concern, and we could redesign or we could modify our design and verify our design right there, then and there on the field. And then there were definitive results generated from the field XRF. So comparing those samples between a fixed lab demonstrated both effective and consistency with using the XRF. Gave us more credence to be able to use the XRF to do quick assessments. So the key was to generating definitive XRF data that could adhere to our quality assurance plan through rigorous statistical analysis throughout the entire process. So the last thing that we want to consider as far as our high-resolution site characterization remedial design is using optimization as a tool. And so EPA has been using optimization for the last 20 years. We've reviewed over about 300 sites here. And so as far as the design is concerned, we're looking at both the design phase and the remedy phase within the optimization here. And so we're defining the design phase as after we've made a remedy selection, but prior to implementation and operation. And as far as the remedy stage is concerned, we're looking at between remedy implementation and operation. So as far as optimization is concerned, we're looking at 7 different aspects, which is looking at the different types of remedy components that exist there, looking at the completion strategy or the exit strategy for the site, looking at sustainability or green remediation options, looking at what kind of data management practices, what data is being collected, currently being collected, and how that's being managed. We're looking at different aspects of the triad approach, which we've been talking about throughout the high resolution modules here. And then what type of monitoring is done, either sort of groundwater monitoring or any other environmental data that's being collected. And we compare that to the conceptual site model. So even though the recommendations between each one of the sites varied quite a bit, there were some common findings during the design. And the first being that there were oftentimes gaps in the conceptual site model. The conceptual site model was oftentimes developed during the early parts of the investigation phase and was not reflective of what the current conditions there were out there. Many of the sites had done modeling, but there were some shortcomings in those models in itself. It was not reflective of either the design aspects or that the current conditions that were sampled during the design did not follow the model itself. In some cases, there were high cost estimates, more than what was predicted during the remedy design, oftentimes to make up or to follow up on a number of different changing aspects to the site after the remedy was selected. And that sometimes the remedy effectiveness could be improved by conducting the remedy in different types of phases. In some cases, they had all the remedy components happening at the same time in different parts of the site, but sequencing those different components was helpful and would provide cost savings and improvement on performance.
OK， 这一堂的课程到这边呢，我们谢谢妹的来带给我们这个半个小时的这个课程啊。那这堂课我想主要也在说明说，调查的应该说从调查的思维到结果跟后面的整治，你怎么去取决于去取舍你这里面的一些部分啦。那当然，其实越细的调查对后面的整治的规划，其实应该是越完整的啊。好，那我们碍于时间，我们赶快接下来下一个还是 Ben 的啊。Ben 他会来针对我们这个高解析度的调查的优劣的分析，跟他相关的资料的判读，然后相关的品管的部分哦，然后再跟我们做一个分享。OK， 好，来，我们OK， 我们就开始吧。
Hello, my name is Ben Benkowski, and I'm going to present a training module on high-resolution site characterizations, pros and cons, data interpretation, and quality control. So where does HRSC, as we call it, fit into the overall process of environmental cleanup? I have a couple of guidelines that I follow. That you need to collect sufficient information to make a remedial decision. Not too much. You're trying to be efficient in this process because the purpose is not to remove all uncertainty. That leads to oversampling and more complicated, harder to understand data sets. For me, it's all about the conceptual site model, the CSM. It should be a dynamic model. It should be revised when you have new data, when you understand better about the lithologies, when you understand better about the contamination distribution. You need to revise your conceptual site model. So with the data you have, can you then make the necessary remedial decisions to clean up the site? If not, what are your data gaps? This can be at the investigation phase or maybe later after a remedy has not been functioning very well. But HRSC is shown to be an efficient way to collect the necessary data, to fill the data gaps, and make that remedial decision. So I've got quite a number of these pros. These are just some of the ones I'm going to cover. The first one, though, that HRSC increases remedy effectiveness by providing a detailed and realistic CSM. You correlate data with stratigraphic and lithologic data, contaminant data. You identify source zones, you understand contaminant mass flux, and you can evaluate plume cores and phaeton transport. It really gives you a more realistic evaluation of what your remedies will be. So one of the things that people talk about as that it's the cost of this additional characterization. It's going to cost more money than you have at the time. But from our perspective, it's money well spent. You can pay a little more now to avoid paying a lot more later after your remedy hasn't functioned properly. Better to know where all those little source areas are and factor that into your decisions. So we have a part of our purpose is to have what we call a green remediation. That is to say, one that has a smaller footprint, that's not, wasteful with our resources. So we think that being right about the site characterization is a step towards a green or environmentally friendly remedy. And then that allows you to make targeted remedies because you know the sites better than you would have without the HRSC. It's very flexible. These technologies are very mobile. You can use them at temporary locations as opposed to a permanent monitoring well. And you get a really high density of data. Borehole geophysical logs have continuous readings. Soil and rock cores give you a very great density of data sampling to understand what's going on there. It's reasonably cost effective as well because the field efforts last usually in weeks, not years or months. The equipment is portable and the field crews are generally small. You don't need a whole army of people to go and collect this information. And as the years have progressed, the technology has advanced. It's come a long way from collecting data by hand. Now it's all done with computers, and you have much greater data density. It's much better to transmit into computer simulations and graphics. You avoid errors in data recording and transcription. And as new information is available, new technologies, better understanding of a particular site process, then the ideas can be upgraded. So because it's all electronic these days, it's easier to manipulate, it's easier to organize, and then turn into 3- and 4-dimensional visualizations. Because once you get the 3-dimensional framework, then you can add in things like groundwater monitoring data and watch the change over time. It's really very informative. Makes many people understand a site finally, because not everybody can take a cross-section and visualize it in their head. It reduces the uncertainty. That's just more data, not too much more data, but the right amount of data will reduce the uncertainty about what's the nature and extent of the contamination at your site. With this reduced uncertainty, you get a greater certainty of your future actions, your future decisions, and what it's going to cost you. So the scale of the measurement is important relative to the scale of the property being measured. When I first started doing this work, we often, when we were using a drill rig, we collected soil samples on 5-foot intervals. And while that may have been good enough for the geotechnical purposes that most people used drill rigs for in those days, you can miss things that are smaller than a 5-foot interval easily that could cause great trouble, could cause great uncertainty in how much mass there is in the subsurface, or where that clay layer is that, has all the contamination in it. But there are, I had to think about this a bit, but there are some drawbacks by having high resolution site characterization. Not everybody is familiar with this technology. There are all sorts of different things that we've talked about and are talking about over these 2 days here. And people don't always understand how they all fit together and tell the site's story. So you have to be careful about who your audience is, because you may need to educate them about what data and what types of investigation you're using and how it all goes together. But not everybody will need to know every detail. You'll lose your audience. You'll not communicate effectively. So know your audience. Don't overwhelm them. It's very useful, but there are some drawbacks. It's not going to give you all the answers all the time. Like right now, we don't really understand back diffusion rates, and that makes a big difference on the duration of groundwater problems. Some chemistry information, you really have to have a permanent monitor well that's properly developed to get a representative sample. And sometimes you just can't, the technology doesn't work. You can't direct push in a rocky environment. Even with there's, bold, loose, partially weathered rock, you just can't get through it. So you just have to understand the limitations. Well, and then there's the human nature part of it, where some people just like the status quo and are able to keep, they prefer to keep going the same way they've always gone. But that's not really a recipe for success. You need to work with folks and have them understand that keep going down the same old path will just end up with an incomplete understanding of what's going on. And there are more efficient, more cost-effective ways of solving your environmental problems. So one of the things about having high resolution data is then how do you interpret that for the other members of the team and your management and the public that are involved in understanding it. Certainly we see as the practitioners the benefit for developing a more realistic conceptual site model. Well, all this matches up well with the data density, and it improves your communication and your outreach abilities. And sometimes just two-dimensional presentations like cross-sections just can't tell the whole story of the site. These are three-dimensional problems, sometimes four-dimensional through time. You may have that much information, but just cross-sections or maps, two-dimensional maps, sometimes just don't tell the story effectively. However, you just can't let the computer do all the work, because it interpolates information, and you shouldn't have blind acceptance. It's really machine learning, not necessarily informed by your years of understanding of what's going on and what's the geology like and what's the groundwater flow like. It's really, you just can't let it go off and then just trust it, implicitly. So you have to make sure that the information that goes in is valid coming out. You don't want to output garbage. You need to know what you're doing. Just don't trust entirely the algorithms or the models. So this is a bit of a cartoon where it talks about a source zone where there are 4 DNAPL layers, what the profile is for those source areas, and then how it might be observed. That's a two-dimensional image. And then how that might be projected onto a cross-section with 4 different vertical profiles on it. And this really is a stepping off point to transitioning from a two-dimensional cross-section to a series of transects which show the plume in 3 dimensions and your lithology information. So I'm going to walk through a series of slides here. So first you have, this is your source up here by this A, and you've got 3 rows of field data collection points vertically. And you get certain information from each one of these borings or direct push locations or sonic drilling the samples and collecting those samples. So you arrange your field investigation to develop these transects, because that's how you're going to end up with this high resolution information. That allows you then to take your lithology data and apply that in this 3-dimensional grid. So you can know where the lower hydraulic conductivity values are, and because that helps control your groundwater flow. So you get those from cone penetrometer logs, or you could get those from actual soil corings that you've identified the lithologies on. But that's a whole, that in itself is a whole data set that needs to be understood and is better understood in 3 dimensions. Once you get your transects laid out, your lithology information put on them, then you can overlay your contaminant concentration information. And in this case, you can see that there is the highest concentration data directly above the clay layer that runs all the way across the transect. You can also project the lower hydraulic conductivity, the clay layer, that's gotten contaminated by matrix diffusion. That's going to be a problem for long-term sources going forward. And then you can see that below this clay, things are really pretty clean. So certainly no source, no very high-level contamination, much deeper. This is another cross-section in that another transect where you add the data. You see how the lithologies have changed a little bit, but you still get the effect of the high concentration data being basically stopped by the clay layer. And all this will go into your understanding in the 3 dimensions, which is when you put all that together, and then you can highlight the highest of the contamination. And then this gives you a 3-dimensional view of the size of the plume and where it would be associated, to know that this 4th boring in this transect is in the center of the plume, but the 5th one is not, or the sixth one is not. And then by the time you get to this 3rd transect, you really don't have any of the very high concentration DNAPL type source material. Because this is then what you use to then understand the 3-dimensionality of the problem and design your remedial system for whatever it is works for this kind of a problem. But you really do need this understanding. It's really that way you're not putting in too many random wells in random locations. You're actually putting in the treatment system, in a zone that you have high confidence that it's going to be effective. It's all about reducing your uncertainty and being more efficient and effective in your remedial design and decisions. So here's an example of a 3-dimensional visualization. This is a site that I got to work on up in a state called Kentucky, about halfway to Chicago from where we work. But the people, the Battelle Institute, devised a scheme where they could understand the distribution of the DNAPL based upon a potential indicator. So the yellow and the green are the highest probabilities, essentially. It's not exactly like a probability, but more lines of evidence that added up to look like DNAPL. But you can see that underneath this chemical plant, there were quite a number of large areas of DNAPL. And interestingly enough, this blue line here is the shoreline, and some of this NAPL does extend offshore. And also over here you see the different lithology layers that can be, projected into the middle here so you can see the lithology and how it's tied to the DNAPL distribution. And all this was done electronically. But they thought they'd go one step further. So this is the same 3-dimensional model, but actually created with a 3D printer. So this is the representation of the DNAPL beneath the site. So these lithology layers are actually printed as separate layers held together with magnets, and then these blue blobs correspond to the blue shapes on the previous slide. This was great for people understanding the extent of the high levels of contamination at this site. It was very useful a very useful communication tool. I wouldn't call it cheap, but very useful, and useful also given the overall cost of the project. It was cost effective, I think, in helping us get to final decisions about this site. So there's one thing that, how do you do quality control measures when you're doing high resolution site characterization? Well, quality assurance is the broader topic of your whole process of going forward in doing your field investigation and analyzing your data and then looking at the results. But quality control really narrows it down to specific activities such as sampling, analytical and data collection procedures. So I've got a few slides here where utilizing quality control in high res is a process accomplished through a series of additional samples or data sets collected with the express purpose of identifying how accurate the first set of samples or data is. This increases the confidence in the quality of the procedures used and the quality of the data collected. For example, you can have field blanks. If you're going to be using a gas chromatogram in the field to analyze groundwater samples or surface water samples, then you would want to run a field blank to make sure that the equipment is functioning properly, that it's clean, and that it shows that it's clean, so that you're not getting any contamination in the environment nearby. When you're using screening tools such as a FID or a PID, those pieces of equipment have calibration procedures to follow. You get calibration gas, and it's supposed to read at a certain value, and that's how you know. That's a quality control step about how you know that the information you're going to collect, say if you're doing a membrane interface probe that has an FID reader or FID analytical step, then you'll have confidence that that data is properly collected, that it is of high quality. So field duplicates, officially it's a duplicate sample collected by the same team at the same time in the same place. But it's kind of a different thing to think about it for high resolution. If you're running a geophysical log, you might run a duplicate section of the borehole again and cross-check the results. If you're using a membrane interface probe, you shouldn't go back down the same hole, but offset by 10 or 20 centimeters and run the section again over a duplicate depth range. Then you can compare the results and make sure that, they may not be exactly the same because you've offset, by a small distance, but you should get general agreement for a duplicate location if you're only moved over 20 centimeters. So that's the end of my presentation about the pros and cons of high resolution site characterization, mostly the pros, the advantages of using this high density data in three-dimensional presentations as better communication tools of what you know, but you need to tell other folks. And then some quality control procedures about how to make sure you've got confidence in your data. There are about 8 other slides. There were some additional information I just don't have time for or time to cover. So those are after this. And with that, Shay.
谢谢。 好，我们再谢谢 Ben 啊，给我们带来今天的最后一节的课程。那这个课程其实也告诉我们，把今天的总结下来，就是说，经过高解析度调查的所有的数据，应用在去建立一个很完整的场址概念模型之后，再去设计你的整治的相关的工法。另外，这个数据的 QA/QC 很重要，因为常常往往没有好的 QA/QC， 其实你拿到的数据是一个可能根本没有办法用的数据，尤其是在现场筛测的所有的设备的校正啊，所有设备的要用这个标准品去做一些查核的工作，这个要特别注意，不然你出来数据你自己都没办法去相信它到底要怎么用。好，那我们是不是进到下一阶段，就是我们今天这一整天的课程的回顾？那我们是邀请到陈老师跟高老师来跟我们美国环保署几位的专家做 live 的一个讨论，好不好？我们请各位老师来，我们往这边走，谢谢。我拿麦克风。
理事长先开示一下吧。
Okay, thank you all our experts from United States. Especially we are in different time zones, so you sacrifice your sleep. So we really appreciate that. Thank you.
好，我听说今天早上非常热闹哈，好像吴老师是用唱名的方式来，请大家提问哈。那我看我们下午是不是就比较轻松一点？我们唱名公司好了，因为我知道今天来了非常多的公司，包括顾问公司、检测公司，还有政府单位哈。哦，你早上唱名公司啊？好，那我们下午就改成唱个人的人名好了。有没有主动等一下提问的时候大声报您的名字？还有我想最主要是公司的名字，让我们理事长还有前任的理事长啊林老师知道有哪些公司这么捧场啊。
我刚刚名单已经看过一轮了啦，大概所有国内的公司都在嘛，很多都老朋友，还
对，
我数了一下，只有6个我不认识，所以
你还有不认识的吗？那我就先那6位先问好了。有没有不认识理事长的？
不是我不认识
啊，对，我想互相不认识。那我们是不是我们最前面最明显的这位卢 Sir 啊？卢 Sir 提一个问题吧，因为您经验非常丰富。
现场工具来，
各位好，又是我，我是 SG 卢泽明啊。那我问一个很简单的问题啦，就是说，其实我想知道说，像美国的话，它在地下水的定义来讲的话，它是怎么定义的？那我问这个问题是因为，像目前台湾的地下水的采样方法，它是规定它是不能过滤的。那不能过滤的结果的造成，说我们在采完样以后，地下水样品再加硝酸，如果你分析项目是要分析重金属的时候呢，可能你的值可能会不管是铁、锰，或者是甚至有一些砷，或者是铬镍，可能都会稍微偏高。那我想知道说，在美国的法规，它对地下水有没有一个定义？它有没有包含悬浮固体物？然后另外就是说，在采样方法上面，因为台湾的地质条件很多都是粉土质或是粘土质的一个地质条件，它里面也比较会有悬浮固体的部分。那这部分有没有什么建议？谢谢。
对，需不要应该 ？Do you understand the question?
You or me?
Go ahead, Ben.
Okay, so we too have problems with suspended solids in samples, groundwater samples. It places a high premium on well construction and the slow purging of the wells in order to not have the suspended solids. For enforcement, we don't allow filtered samples. We allow filtered samples in understanding the characteristics of the groundwater at a site, but it's not part of what we would use for a legal decision at the end. Matt or Tim, you got any more to chime in on that?
No.
For me.
没关系，我想我们可以又问第二个问题哈。他们在思考的时候，或者在翻译的过程中，有没有其他的问题？啊，你不要问那么多了，你问一个就好。
吴老师先想一下，我利用这空档先问他们一下。
Okay.
I do have a question regarding we should filter the sample or not, because sometimes there's a controversy regarding, in particular for heavy metal. Sometimes if you don't filter the sample prior to the analysis, the concentration values sometimes tend to be very high. But if you do filter the sample, the concentration of the groundwater may meet the regulation requirement. So I'm not quite sure for all you gentlemen, do you think filtration will be a necessary criteria?
I think if you're doing groundwater screening, then it would be okay to do filtered and unfiltered. But if you have a permanent monitor well installed, then you should not have a filtered sample. You should be able to design the well with the right size sand pack and slot size to not have turbid samples.
So in US, is the filtration required or not? I believe it from the responsible party point of view, they want to see the sample is filtered, right? So they can get a lower value for the groundwater sample, I guess. But from the agency point of view, probably in the opposite way. So what do you think?
I think you're right. And for screening, it's okay to do both. But for making remedial decisions, you need to have permanent monitoring well data that's unfiltered.
有没有其他的问题？
Yes. This is Tin Lian Wu from Queensland University. I have a question for Ben. And you introduced the dye LIF technology. And what kind of the dye you are using? It's only oil ray or some other dye? And your slide in your presentation 860, you mentioned the dye LIF response. Dye LIF produce equivalent an all-year rate of shake test at 0.5 centimeter spacing. Have you ever conduct the all-year rate of shake test? Do you have any experience how to do the test? How to conduct a test?
So I had a dry cleaner that likely had DNAPL present, and we did have continuous cores. We segmented and mixed with the O-red dye. So it is used, but fortunately, many of our sites don't have undiscovered DNAPL. It's kind of that's really when you're in the very beginning of understanding what's going on, your initial characterization.
在座的各位先进还有没有问题要提出来讨论的？中英文都可以，没有问题。
Hi, good night. And I have some technical question about the ISM incremental sampling method. The first thing, does it can apply to the VOC contamination? And the second thing, we see when you get the soil core sample in the liner, you cut off the top of the liner and then taking the sample for further analysis. Does the result affect the VOC concentration, or does it can be, I think, to be representative of the VOC concentration? Because we know if we in our EPA's Taiwan EPA standard, if you cannot disturb the sample in the liner before analysis. So if we cut off the liner and take the soil core sample, small subsample, is it okay, or it is acceptable in US EPA?
So the question is, if the liner has been cut off of several sections, will that affect the VOC result? Will that interfere with that?
Tim, you're on mute.
Yeah, I was on mute. That's a great question, and it does require some diligence and care to make sure that you're not releasing the volatiles. But so we try to keep the sleeve, the liner, as intact as possible. If you're taking multiple samples throughout that core, sometimes it helps to have multiple people doing that. Where when the sleeve is cut, we're immediately taking the plug and placing it in the solvent for analysis. And naturally, that would require a lot more of the solvent than we would normally use. So that's another consideration.
Tim, on a basic level, you can't do incremental sampling for VOCs, can you?
Yes, you can, and it has been done.
Okay.
And again, it requires just a lot more care, some more advanced planning. You will have to cut the liner in order to get to the section that you would like to remove from the DPT sample core, but it can be done, and
again, it just requires a lot more care and planning.
Thank you.
各位还有没有问题？
I have two questions. One is simple. Many of you mentioning what's called DU, decision unit. I guess it's only for soil sampling. Do we have a design unit, decision unit for groundwater? That's the first question. And the second question is that based on your presentation, you know, most of the time in real situation, there is a so-called cold plume going from the source area to the down gradient area. It's just like a long sausage. It's not a fan shape. So when we know this nature, and coupled with this transect design, should we do the transect design in sequence? Say that near the source area, let's design the first transect and identify the location of a cold plume. Then a few days later, then we design the next transect down gradient, and maybe we can narrow down the width of the transect. But this is based on the ideal situation that the cold plume will move pretty much like a linear direction to the down gradient. If we have an odd situation, say my cold plume starting from the source area, then dive to the deeper area, and oddly it might, switch, say 50 degrees off the central line, then this will cause some troubling. So I'm curious, how do you design this transect? Do you plan at the beginning just, have the whole set, or can we do this in sequence that based on the previous results? Thank you.
Well, I have a site in Miami that had the same problem. And you need to be flexible. One of the lessons I learned from that site is I put transects, once I started seeing how big the plume was going to be, I didn't change the spacing of the transects. So we spent extra money that we didn't have to characterize the plume. I would have spread the transects out farther during that initial characterization. But no, there's not really decision units. It's all the aquifer all needs to be restored. You need to understand the contamination for all of it. So it's not just this part over here is not a problem because nobody's using it. It all has to be characterized and understood the same and cleaned up the same.
I would agree. I would say that decision units don't necessarily exist within groundwater per se. But as far as the understanding the sequencing between doing your transects, I think the key part of it is understanding, understanding your CSM, understanding what information that you have out there, either that you have, existing monitoring well data or drinking water well data, and then, trying to find exactly where that core of that plume is. So, the way you had outlined that initially by going from, from the source down gradient is a good approach if you have no information whatsoever. So Yeah, it can be really difficult to figure out where that core is, because that's so critical in terms of thinking about the design, and when you sort of think about the recipe and focusing either an extraction method or an in situ method.
大家好，我是工研院许欣兰。首先谢谢3位今天精彩的演讲哈，我们有听到蛮多的就是关于就是高解析调查的一些工具。那其实有蛮多的工具是要获得垂直向的，比方说污染分布嘛。那会用到这些工具呢，其实一方面是为了想要避免垂直向的污染的混合。那我想要请教的问题是，我们在做一个场址之前，有没有什么样子的一个评估方法，可以告诉我们说这个场址需要用到这些特殊的工具，以避免这个垂直向的污染？谢谢。
Well, I think you have to start someplace and just be very careful. You got to poke tools into the ground, and you never know what you're going to find. You can think about what you're going to find, but you could easily be surprised. And so you just you need to, if you were using a membrane interface probe, and you find that you've got a very large area of contamination, then maybe what you would want to do is pull out of the hole and quickly cement that up rather than allow further cross-contamination. Some of it you just can't avoid, poking holes, and that's how you have to collect the data.
I would agree. I think there is always this concern that you might be doing more harm within the subsurface, but there's ways to mitigate that, because the information that you get when you do those borings is oftentimes much more valuable in terms of thinking about, understanding the pathways and then applying those, and then determining whether or not you need to take action or not. So that all goes into thinking about whether or not you need to spend money to mitigate the problem there.
我们时间也快到了，还有没有什么其他的问题？
I have a question about Ben. 在slide 的第4至74 page， you talk about the diffusion bag sampler. You mentioned that 它可以应用在 metals 跟还有个 MEE parameters。我不知道这就是 metals 就重金属。然后还有一些6价弱的一些调查，我比较好奇它是怎么有一些扩散机制，可以在这种被动式采样带可以应用。然后在同样这样 slide 这种 MEE parameter 它是什么？我刚才好像没有听到，可不可以再提醒？这是什么英文字的缩写？
may look at my presentation.
The gentleman is asking the question in slide 4-74 regarding the polyethylene diffusion bag sampler.
Okay.
And he's asking the he's curious about the diffusion mechanism regarding metals.
Okay.
And what is the MEE stand for? The MEE parameters. The MEE on the slide.
See it. And I don't remember off the top of my head. I'm sorry.
That's okay. That's a midnight.
But it's, some people like to use these diffusion bag samplers maybe for 10 or 15 years now. But most everybody still samples monitoring wells the old-fashioned way. So I don't, because you could wonder about things like PCBs. You just don't know how well they would diffuse through these liners.
各位还有没有什么问题？
你好，我是瑞常科技何哲豪。那我想，我是看到后面有一个那个技术的介绍，就是有关地下水跟地表水的那边有一个热影像的技术，还有一个 DTS 的这个技术。我想请问一下，这两个技术除了应用在简报讲的地表水跟地面水的这一些调查之外，在光土壤地下水之外，是不是还有其他的一个应用的一个美国实例的一个应用的范例？就是跟着后面78、4至78、79、78之后。
Right. I like it about if it shows the connection between the groundwater and the surface water. It has some limitations though. It only really works on the surface. You have to use perhaps a temperature probe to stick in the water and into the sediments to get some deeper readings. But because it uses the infrared, it shows you things that you wouldn't know otherwise. I think it's most useful in that groundwater to surface water interface, defining that. I think it's going to be part of one of the case studies tomorrow.
I agree. I think it's a good screening tool, and then you certainly can follow up once you have identified an area where there is some flux, either it's a gaining portion or a losing portion. You can sort of isolate whether or not that's consistent, from a seasonality standpoint.
还剩下3分钟，所以可能还有1、2个问题。 许博士。
不好意思，我是可以补充一下刚刚没有办法回答的那个 MEE， 因为我快速 Google 了一下，它代表的是3种气体，就是M 就是 methane， 然后2个 E 就是 ethane 跟 ethene， 就是甲烷、乙烷跟乙烯。
所以你那个位置是有网络的。
Sounds right. And because that's, if you think about it, those are the gases that are produced when TCE or PCE degrades. So you're able to see that as a measure for the breakdown of your VOCs.
From the supplementary information of the slide, you mentioned about freezing soil core sampling method, and it can be applied to the microbiology. So, is any in this talk, in today's talk, we did not mention much about the microbiology. Is any application of the microbiology sample or sampling methods for the high resolution site characterization in United States?
I think we're doing more and more of it. It's just amazing what you can understand about what's going on, about why things are degrading or why they're not degrading, and designing remedial actions to clean up your groundwater by knowing the microbiology in the aquifer. It's kind of expensive, so I don't know that people would do high resolution sampling for these microbiological parameters. Usually it's after you do some sort of screening steps or after you have some monitoring wells installed. Matt, do you know of people that have done that for high resolution?
No, not typically, but you do need to have a baseline information to be able to get an understanding whether or not it would work or be as a potential remedy. But I've not seen it as part of in tandem with high resolution.
So maybe the cost is the major issue, because the expense for doing the microbiology diversity analysis, sometimes it costs a lot of money. So maybe.
And I don't think you need that information in the beginning when you're doing your site characterization. You need it to do your remedial design or to consider your remedial actions. But you don't usually need it to know the distribution of the VOCs. It's really more of a second or third step.
Yeah, typically it lends itself much later in terms of design. And once you've established, sort of the extent of the plume and getting an understanding of where potential cores are, where areas are the more absorbed versus other areas.
我们是不是最后一个问题？在座的各位。
Since President Chen just mentioned about the cost, so I want to ask you a question about a quick question about the cost, because during the coffee break, I heard some attendees, they talked about a cost analysis. So they are curious about the cost by doing this high resolution site characterization, because according to your slides, looks to me, we need to punch a lot of different holes, and we need to use a lot of different fancy toys. So looks to me, they are not very cheap. They are very costly. So in that case, do we really need to use these technologies? Because Taiwan, compared to US, Taiwan is a small country. Certainly, compared to Singapore, we are a huge country, but compared to US, so for most of the sites, the driving distance from the site location to the commercial lab is maybe less than 30 minutes. So do we really need to get the real-time data on site?
Well, I think it's more in terms of understanding quickly where your contamination is before you install your permanent monitoring wells. 30 years ago, we just went out and drilled wells, permanent monitoring wells, and maybe they were in the right place or maybe not. And that's not cost effective. I've come to believe that the money that you spend in this high resolution screening steps lets you make a better decision about where to put your permanent monitoring wells without having to go. It used to be you would go to the field, drill a bunch of wells, take some samples. 3 months later, you'd look at the data and make plans to go out there again. But with this method, you can go out and in the matter of a couple, 3-4 weeks, you can get a pretty good handle on how big your plume is with screening data and not cost the additional months or years in characterizing your site. So I think it's cost effective in that way.
I would agree, and I would also add that lessons learned that we have seen through the optimization program have shown that if you don't have a good idea of the conceptual site model, if the investigation is sort of shortchanged, and there's resources put into doing site characterization, the design could be significantly impacted. There are sites where that investigation was really rushed and it missed the plume core, and we installed a very expensive system or a very costly system, and that system just runs, and we never find to a point of meeting the performance standards in itself. So it has huge implications in terms of being able to design, adequately design, and target the core, the plume core, so that you get to a point or a final point and closure of the site in itself. So the other thing I would add is that so many of our technologies really rely on making some sort of contact. Like if you think about an in situ chemical oxidation remedy, the chemical has to be in contact with the contaminant, and so if you don't know exactly where the contamination is or where the core is, you're potentially sort of designing something that is not as effective as it possibly could be.
Actually, a case study about that tomorrow. So stay tuned.
Okay, so we look forward to seeing you tomorrow. And I believe it's 3 o'clock in the morning in Central Time Zone, 2 o'clock in the Mountain Time, and 4 o'clock Eastern Time Zone. Okay, so try to get some sleep, and we will see you tomorrow. Thank you.
Or later today, actually.
Thank you.
Bye.
非常谢谢各位伙伴今天来参加这次的会议啊。那我们也特别谢谢两位这个土水协会的理事长跟前理事长高老师跟陈老师协助主持。我们是不是鼓掌？这个谢谢他们一下好，谢谢两位。好，那因为时间的关系，我想我们就不占用各位的休息时间。今天非常谢谢各位撑到最后那明天我们还有一天也是相当精彩的一个 program So I will see you tomorrow。明天OK。好，那明天见谢谢。谢谢。